extra time has begun. It's hard not to play alone. Baby, it's crazy.
so much you on my mind. There's so much money and pussy and you think I'm going blind. I think it's funny how blogs talk. Funny how many shows I had went to where models walk. So many stories about you and so who from Harlem. It ain't too many from Harlem, so take a guess. Taking a jet so I can recollect. You say what's up with your baby, I always say what's next. I mean, what is we in it for? Revenge from your friend's circle, like what did we enter for? Tired of fancy dinners, I'm tired of diamond balling. I'm tired of hearing about if this nigga put hands on you. Tired of trying to smile through shit that's affecting us. Then I get to overthinking if I'm here messing up. Mac died and I couldn't talk, couldn't bear the thought. 2 days before what we was talking about love and loss. Then he mentioned Ariana mama in newer songs. Never told her so, but I knew he was dead all alone. You do something to me. I write all my songs about women I never keep. I hate when I have to lose them, I hate them when it's deep. You one of my 6 women that's in the east. I hate making promises that I never keep. So promise to never ever be too patient with me. Just promise me. Love and loyalty, that's over honesty. The devil be talking, but God controlling me. Rock Nation dinners that inquire about me. My God the realest, that's how we meet.
trying, we keep hanging on. Patient and wrong. We keep trying, keep on keeping on.
Days fly till you're alone. Always counting down until we stop listening. Can drown it, I don't wanna apologize. Posters on my sleeve, now that I recognize. I keep it to myself cause I'm preserving my life. I didn't even want you to know. Shedding my fears when I needed the most. Never forget what I'm still holding close. Still hanging on to the moments I chose. Every single day I feel the moments won't last. I won't be back. Stitching up my memories and I'm in between. I won't be so petty cause I know you're right. Cause shaking on the blueprint right upon this line. I'm loosening my grip cause I believe it's alright. I didn't even want you to know. Shedding my fears when I needed the most.
Your magnetic connection is pulling me in. I tried to fight it, but I can't escape it. Your energy surrounds me. I love your atmosphere. When you're away, I can't wait till you're right back here. Baby, I need you here. Baby, I need you near. Baby, I need you near. Baby, I need you here. Oh, this distance is slowly killing me. I can't take the thought of you being so far away. 'Cause I need you here, and I want you near. 'Cause don't you know that I'm hurting? Oh, baby, I need you near. Oh, baby, I need you near. I need you near. Come back, I miss you, baby. Come back, oh come back, oh come back to me, baby please, baby please. Said I need you, yeah. Baby, just say yes. Baby, please come back. Yeah. Baby, please. I'm begging you, please. Wanna see you. Nobody else can see, no. I need you, baby. Oh, I need you, baby. So you leave me too, baby. Tell me what you wanna do. 'Cause I miss you. Yeah. I miss you. You found my love when you found me. 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 You're my lemon tea, you're all I need in me. You got the right ideas, will you hold on to me? You're my lemon tea, you're all I need in me. You got the right ideas, won't you hold on to me? Will you hold on to me? Hold on to me, hold on to me. I color you in, and deep into the creases in your skin. It means a lot to me, so I try. Yes, I try. I blend into the shade you knew. I wondered if I was still the color blue, 'cause I always think of you. Oh, 'cause I always think of you. You're my lemon tea, you're all I need in me. You got the right ideas, will you hold on to me? You're my lemon tea, you're all I need in me. You got got the right ideas, won't you hold on to me? You're my lemon tea, you're all I need in me. You got the right ideas, won't you hold on to me? You're my lemon tea, you're all I need in me. You got the right ideas, will you hold on to me? Will you hold on to me? Hold on to me. After a rainy and I need you by me, baby. Every
I hope you know how much you mean to me. In every way you make me stay, I'll be needing you. Holding you in my arms is all I need in my Sunday morning. Baby, you're all I want, so don't you let go of me. You're beautiful like sun rays after a rainy day. And I need you by me, baby. Every day. Ooh, 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 every day. I need you by me every day. Me love for you there, me love for feeling, say Jimmy, baby. They there in me, I know, so don't be me and feeding, holding me, prize on me, bossy me, prize on me, yeah. You're beautiful like sun rays after a rainy day. And I need you by me, baby.
Turned on handheld. So this is handheld 1 or 2. Yep. Okay. This is handheld 1 and 2. This should be lead vocals 1. No, 2, I think. All right, now turning on the last one. Yep, that should be lead vocals. Yep. Okay, cool. Nice.
focus on the things that matter most to me. Like the day you told me that you loved me just for me.
I'm trying to be a better me.
Sing it with me, y'all.
I'm trying to fix myself so we can be happy. I'm trying to be a better me. I'm trying to fix myself so we can be free.
Trying to build a future so I leave a legacy. Trying to show myself the miracle that I can be. Trying to take that knowledge, share it with the world. You see, we can't be greedy, it is our responsibility. Trying to be like you, a kind of loving mystery. Even when I'm wrong, you always see the best in me. You inspire me and maybe see the future me. A man who speaks the truth and wants to raise a family.
I'm trying to be a better me.
Sing it with me, y'all.
I'm trying to fix myself so we can be happy. I'm trying to be a better me. I'm trying to fix myself so we can be free. I'm trying to be a better me.
Sing it with me, y'all.
I'm trying to fix myself so we can be happy. I'm trying to be a better me. I'm trying to fix myself so we can be free. Suddenly, my heart is yours, lovingly. I let you know I left the world behind. Oh, I told the stars you're mine. Why'd you tell me to walk away? Oh, what if I don't need no space? Oh, you just need some confidence. You just need my company now. Even if I'm broken hearted, I'll still stick around.
Okay, let's get things underway. Please take your seats, and we'll start proceedings. So my name is Nicholas Lane. Welcome to the Flower.ai Summit for 2024. For the next 2 days, we're going to make fantastic progress together on ideas such as decentralized learning, federated learning, and privacy-preserving machine learning. And I can't wait to see what we can accomplish over the next 2 days. What's fascinating to me about this event is that FS24, as I like to call it, is now the world's largest federated learning conference. It's been going for about 4 years now. And each year, it basically doubles in size. For every person you see in the room, there's 6 other people watching online. And for the first time, we crossed easily over 1,000 registrations for the conference. So I'm tremendously enthused. We have people coming from all around the world, China, Europe, the US, just to present work that they've done advancing this area. And I just can't wait to see what happens over the next 2 days. This event only lasts for 2 days, but for the rest of the other days of the year, the real foundation of what we do is you. It's the Flower community. And so the Flower community that powers everything that happens here really has kept on growing year by year. We now have over 120 different individuals contributing code to the Flower ecosystem. We have more than 3,400 active developers in our Slack system building on it, and more than 1,200 independent projects exist that build directly on Flower and reach towards the stars for doing things in the direction of decentralized, federated, or privacy-preserving learning of various kinds. And of course, we've 3,900 GitHub stars so far. Essentially, scientists and AI devs love Flower, and we can't be more enthused about this. And what really makes me excited is the fact that we finally can start to see 2 critical parts of what we call the Flower hypothesis. For many years now, federated learning has somewhat been maligned as a niche technology. But as you'll hear from Daniel pretty soon, we believe that it can be everything that machine learning needs in terms of being able to service societal goals and advance machine learning towards better and more powerful models for us all to benefit from. And the way we think we can make this step change is by driving it through community and easy-to-use tools that up until this point have not been available. And so as we start to see this critical mass of the community evolve, as we start to cross these boundaries, such as having 1,000 people at this conference, we can start to see this hypothesis play out. Last night I was looking through the registrations of who is going to be here. And so, for example, if I look at academic institutions, you can see many of the top universities in the world use Flower to do their research. Many of the people are going to be presenting work to you today at the stage, but they're also in the audience. We have also a large number of core industrial and commercial companies looking to deploy this technology. And finally, we have big tech of various kinds looking to use federated learning to advance what they need to build. And so what the main message of this slide is that everybody who needs to be here is here in the next 2 days. I encourage you to talk to one another to see how you can advance your research ideas, how you can advance adoption in this space, and let's see if we can make this event truly historic. Let's talk about what we're going to see the next 2 days. Today, the focus is AI research. And so there's a lot of open problems in the space of federated, decentralized and privacy-preserving technology. We're going to hear very shortly from Daniel, who's going to start to talk to us the progress we've made in the platform that allows you to make those advances more easily. But essentially today we're going to have 13 different talks, 17 posters, all focused on open research within the space, and this is going to be combined with the second day focused on industry, where we're going to see a similar number of talks and posters, but more focused on industry experience, best practices, and adoption. And so with that, I'm happy to hand over to Daniel. He is the co-creator of Flower, and he's going to lead things off and tell us all about the massive progress we've made in the platform for us all to benefit from. So over to Daniel.
All right, thank you very much. It's really incredible to see so many of you here today. It's not that long ago that Federated Learning felt like sort of the best kept secret in AI, and to see so many of you here today is really exciting. Welcome to the Flower Research Update. The team has worked incredibly hard. We have many things to share today. Thanks. And I can't wait to share those updates. But before I go into this and before I show what's new in Flower, I want to give a little bit of a background of why are we actually working on this. So the natural state of data in the world is it's distributed. Data is distributed across different organizations. It's distributed even within single organizations, for example, distributed across different regions for regulatory reasons. And it's distributed across user devices. So some companies, they have users, they have billions of users, and all of those users have some of the data. So this is just a natural state of the world. Now, if you look at machine learning as it happens today, usually the training happens on only just a single of those data partitions. And there's so many of them. So people are talking about GPU-rich and GPU-poor, but you could almost more important than this is probably, are you data poor or data rich? And clearly, as you can see, most of today's machine learning workloads are data poor. And they don't have to be. Healthcare is a prime example. There's a lot of healthcare data in the world, but it's partitioned, and no one has access to large enough quantities to train meaningful models. Now, collecting data is the usual approach that people try to do. They try to collect as much data as they can to make one of these partitions larger, but as we can see, this is a very limited approach. It's just unrealistic to collect way more data. Yes, you can make a licensing deal with a different company, and maybe you get access to some training data, but the vast majority of data will still be inaccessible to you. Federated AI at least has the potential to solve this. It's something that I think many of us are excited about and many of us are believing in and working on. And it solves this fundamental challenge by, instead of trying to move the training data, it moves the computation to where the data is. So we don't have this challenge anymore that we have to move the training data. It can stay where it is. It stays distributed in organizations, distributed across different user devices. But then we move the computation there and we allow organizations and users to keep control of their data. Now, there's very different flavors of federated systems. A typical one that often gets mentioned in the press is cross-silo multi-organization. So multiple organizations collaborating. Prime example is multiple hospitals trying to train a model together. The other extreme is sort of cross-device, multi-user federated workloads, where you have a single organization, they have potentially billions of users, and they try to train models on those devices. Some other flavors that we also often come across, but that don't get as much attention usually, are cross-device single users. So for example, in a single factory, there might be multiple machines producing massive amounts of data, and it's just more practical to federate the training across these machines. And then yet another one is single silo, single organization, cross-silo, single organization, where you have a single organization that has data, for example, in different regions. As for AI research, we strongly believe there's this virtuous cycle between research and industry. Researchers, they try to experiment with new approaches that can blow up any second, and then once something starts to work, industry tries to deploy this in production. and at a scale where the servers easily could catch fire. What does great research need? We believe it needs flexibility. Researchers want to customize every aspect of their workload. It needs performance. You want to run large-scale simulations, and you want to run many of them in a short amount of time. And you need an ecosystem. You don't want to re-implement all the papers that are out there from scratch, but you want to rely on a large collection of data sets, models, aggregation strategies. In 2023, we had a number of meaningful ecosystem launches. We have Flower datasets, the largest collection of datasets in Federated Learning. We launched Flower Baselines, the largest collection of baselines in Federated Learning. And you'll hear more about those in separate talks throughout the conference. To the first announcement of today, we're announcing Flower Discuss, a new community forum that brings the research community together. And you can join it today. It's the URL is discuss.flower.ai. Sign up and join the conversation. Benefit of the new forum is conversations are much more permanent compared to our Slack channel. So you can easily search all the conversations and bring up all replies that easily get lost in Slack. So what's next for the framework? Today we're announcing the Flower Next preview release. Last year we talked a lot about the driver API and the first prototypical release of it. This year, Flower Next is here. And I want to go into a first demo. What you'll see here is a new command called flwr new that allows you to easily create a new project from scratch. So you'll give it a name, and then you can choose from a number of templates. And then you get some help in how to actually run the project. So we'll cd into the project. We'll install dependencies. And after that's done, we can simply type flwr run, which is the second new command, and run the project. While this is running, I'll quickly show you the code. What this created is a directory structure, fedlfg, and in that you have typical requirements txt, and you have a typical Python project with a init.py. You have your, because we chose the PyTorch template, you have a typical PyTorch project with a simple model in this case, you have some data loading functions, a training and a test function, and just a typical Flower Hello World project. You also have a client.py, which has your typical Flower client included, and it has a new thing called client app. Client app is how you can see that this is a Flower Next project. And then for server.py, it's similar. You have the strategy. In this case, we're just using federated averaging. And you have a new abstraction called server app. And that's how you see that the server app is compatible with Flower Next. Let's go back to the logs. We can see this is still running. It already performed a number of rounds. We also updated our logs to make them easier to parse visually. The strategy sampled the 2 clients that we're simulating. It received results. It aggregated those results. And then it went into the next round. So that's Flower New and Flower Run. What about all of those features that we often get asked about? What about differential privacy, secure aggregation, logging to weights and biases, or TensorBoard, or MLflow, how to measure bandwidth, how to measure the number of parameters that get sent back and forth, how to do checkpointing? Well, today we're introducing Flower Mods. Flower Mods is a key feature of Flower Next. This is what a typical client app looks like without Flower Mods. So you have your Flower client and then the client app thing. Now, if you want to add differential privacy and secure aggregation to that, it's just 3 lines of code. You need to import the respective mod and then add the mod to your client app. And that's how you can easily add things like differential privacy, secure aggregation, but also many other things. So in the initial release, we'll also already release a number of built-in mods for differential privacy with fixed clipping and adaptive clipping, local DP, SAGX, SAGX+. We'll have some utilities to track message sizes and number of parameters. And then we also have a bunch of other mods coming soon. For example, logging to weights and biases. Let's go into a demo. I prepared a small mod, just a Hello World mod that literally just prints two statements, one before the local training gets executed and one after that. Now we need to import it. So from fedlfg.hello world, import the Hello World mod. And then, oh, that's the wrong file. This is how you can see that that's a live demo. So this is the client, and then on the client side, we simply say mods, and we add the Hello World mod. Now let's run that again. We can see it's starting again, it's launching the Ray backend. And now we can see that the two clients are already putting out the first log. So this is the hello that happens before the local training runs. And it takes a couple of seconds, the training runs, and then after the training is finished, both clients print the second log, which is flower.ai Summit. And that's Flower mods. Next, we're introducing the message API preview release. This is, last year we've talked about the driver API. The message API is the driver API on steroids end-to-end, both on the server side and on the client side. On the server app, you'll get access to a driver object that allows you to send individual messages to individual clients. And this allows you to do many things like async FL, cyclic training. You can use custom for loops. You can implement custom workflows and really use this to implement arbitrary protocols on the server side. The client side and the client app supports basically the mirrored side of this. So with the client app, you can register functions at app.train, at app.evaluate, and at app.query. That's a new functionality for Federated Analytics to provide that in a more structured way. And then you can access the exact same message that you sent from the server side, you can access it on the client side. This also enables you to have stateful computations on the client side. There's a new context, and context has state, and you can change that state. And that state only remains on the client side. So it's up to you to decide which part of your data should, which part of the basically of your local training state should remain on the client side, and what are things like evaluation metrics, for example, or model parameter updates that you want to send back to the server. This all builds on a new abstraction called record set, and record set is similar to what we had before with fit instructions and fit results, but it's much more powerful. It easily allows you to add multiple models and send multiple models. It allows you to send multiple sets of metrics and multiple sets of configuration values. What about LLMs? LLMs have proven to be incredibly useful for a wide range of tasks. And of course, we want to make Flower the best place to train federated LLMs. Today, we're announcing LLM Flower Tune. It's a friendly federated LLM fine-tuning capability. I'm going to start the demo and then introduce what you're seeing here. So this kicks off the LLM fine-tuning process. And what we're seeing here is a distributed setup, of course, with two data partitions. We have two machines running in the US. And both of these machines only have a single GPU. And they're running, we're supporting Llama 2 7B and Llama 2 3B. For the sake of this demo, we're using 3B to speed it up a little bit. And what they do is they perform federated fine-tuning, parameter-efficient fine-tuning with LoRa. And it's incredible to see how easy to use this is. And it's something that many organizations reach out to us about and are very interested in because many organizations realize that they have some data internally. There are LLMs out there, but those LLMs don't exactly do or don't perform extremely well on those tasks that those organizations are interested in. So this is a way to privately fine-tune LLMs on your sensitive distributed data. If you go back into the demo now, this is a little bit cramped because the font size is big so that everyone can read it. But you can see the training already commenced. And it started on 2 clients. And if we wait long enough, we'll see those results come back from the 2 clients and then get aggregated on the server side. And because we're using PEFT with LoRa here, the updates that get sent back in exchange with the server are actually rather small. So we don't have to send the full 7B or Llama 2 3B model over the wire, but we're only sending pretty small updates over the wire that can easily be exchanged. All right. That's it for FlowerTune. All of what I've shown today is available in Flower Nightly. So this is not something that will come in a number of months or anything, but you can really go to PyPI, download Flower Nightly today, and use all of this. The full rollout of Flower Next will happen over Q2 2024. We're inviting everyone to try this out and to give us feedback, and we're working this feedback into the full rollout to make this a nice experience. In terms of roadmap, Flower Next rollout is the most immediate thing. We'll launch documentation for all of those features over the coming weeks. There's already a few code examples that use Flower Next, so those are the best resource for now. But of course, we'll add full documentation and tutorials for how to use all of this. For LLMs and FlowerTune, we'll also take the next steps, and we'll gradually expand the range of what FlowerTune can do. Simulations will only get faster. We built in support for multiple backends. Right now, we're using array-based backend. We have a number of other experimental backends that prove to be incredibly effective. And we are planning to use this to support very different simulation environments. So if you already have a large-scale cluster running, Flower is the best tool to integrate with that. And of course, as always, we'll provide more baselines, more data sets, and more mods. And that's it for the Flower Research Update. Quick summary is Flower Next, FlowerTune. Join discuss.flower.ai and take care of the incredible opportunity we have in going from data poor to data rich. Thanks.
We've got time for questions, both in the room and on Slack. Oh, let me...
Okay, 2 very quick things. So with the Flower New, is there capacity to have customized templates? And second, with regards to FlowerTune, what are the supported model architectures? Is it just Llama 2, or is there more supported? And how easy or hard would it be to add support for different architectures like Mistral and so forth?
Great questions. For Flower New, currently we have a couple of built-in templates. This is all open source, so you could easily contribute a new template. We don't have support for custom templates yet, but it's a great idea, actually. I think we haven't thought about that yet. I think this is something we could add. For different model architectures, it's actually super easy to exchange different model architectures. We just announced Llama 2, those 2 different variants, or actually 4 different variants in the example, because those are the ones that we verified, and we ran some benchmarks, and we published some performance numbers for them. But it should be incredibly easy to just switch it out to a different model architecture. It all builds on Hugging Face transformers.
Charles, anything in the Slack? I promised that we'd engage with the online folks a lot, so I want to make sure we give them a chance.
Just someone asking if the slides will be shared online. I don't know.
Yeah,
to us.
But the videos will be. I guess the clean answer is the videos will be shared, so that's how we'll deal with that. Any other questions in the room? Otherwise, okay. Let's thank Daniel. Thanks very much. So that was our first internal talk of the day, but I'm really happy to introduce Andrew Sultan. He is going to be our first external talk of this session. And so, so Andrew, just plug on in there and start to set up. And while you do that, I can introduce you. You just need an adapter. Yeah, okay. So let me tell you a bit about Andrew. Andrew is a fellow in the Clinical AI and Clinical Artificial Intelligence and Specialty Register in the Medical Oncology at the Oxford University Hospitals NHS Foundation Trust. He is also dissertation lead for the MSc in Applied Digital Health at the University of Oxford. But I first got to know him from a tweet. And so this really speaks volumes for how easy it is to use Flower. So Andrew here, working with his colleagues, worked away on something they call Curial AI. And so Curial AI was an AI screening test for COVID-19 that used the vital signs from folks. And so within 1 hour of the person arriving in the hospital, they could give you a first early indication of if you had COVID or not, driven by this AI model. And what was interesting about this is that he built this system on Flower. And so this system, working in 4 NHS trusts, processed 130,000 patients' data to build this model. And so it was a proof of concept of the power of federated learning and what happens when you go from being data poor to data rich. And he did this all without us being involved. He just looked at Flower and his own initiative, and he had this amazing idea of using Raspberry Pis. And so this is what he's going to tell you about in the next few minutes. But with that, over to Andrew. Thank you so much for your contribution.
All right, thank you. And thank you, Nick, and thank you, Dan, for having me. My name's Andrew. I work as a medical oncology trainee at Oxford University Hospitals Foundation Trust and a researcher at the nearby university. And I love Flower. And what I'd like to do today is tell you a little bit about some work we've been doing over the past few years, including using a piece around federated learning using Flower back in 2022. And I'm delighted to see all of the new shiny features today and actually what's come a really long way since. And perhaps talk a little bit about future plans and future ideas in the research field. And so when thinking about how to approach the question of effective and clinically safe AI, typically we've got the problem of data siloing, cross-organizational data siloing, where data is held in multiple hospitals, and despite us having a nationalized health service in the UK, the hospitals typically will have no sharing of information between them that's electronic. There are some limited systems, but on the whole, data is held within silos. But to develop models, the AI researchers typically will be in a university, which is a separate organization, to the hospitals, or in a company, or you may wish to work with data from multiple countries. And traditionally, what would have been done is to apply for an ethical approval to move the data to a university or move the data to a hospital. You'd clean it, you'd develop your models, and then you'd go on to validate it and roll it out. And of course, as to preach to the converted, there are problems with that, both in privacy, but also in logistics and in entrustment. And the federated learning paradigm really helps tackle some of these issues, where the data never leaves the hospital and instead we move the compute to the data. Now, there has been some work around that in the past in the literature, most notably Diane et al. In Nature Medicine was one of the very first pieces to actually, in the real world, build and implement an AI model using federated learning, and that was done with the support of NVIDIA. And when I first prepared these slides, they had a valuation just under $2 trillion, and I realized on the train down today that that's gone up by more than the NHS budget in the last couple of weeks. And they, to do the study, will have had considerable resource for them to be able to develop these models and implement them. That includes providing technical support to the individual hospitals involved. And the difficulty with that is it doesn't scale readily if you're dependent on providing technical support to hospitals. And we really wanted to make something that was very easy to use, and we were helped by a very easy to use framework so that we can then use this in the NHS and the real-world healthcare setting in the UK as a proof of concept. And there's been some other work from Intel and colleagues as well, trying to do some medical imaging work with the OpenFL library. Now, to give you a little bit of background, at the start of 2020, when COVID came along to our emergency department, we were faced with the issue of it taking initially up to 3 days to get a COVID PCR test result. And at the time, the cost was around £200, although the turnaround time and cost have come down dramatically. And typically, when a patient came to hospital, as almost a package, a standard package, everyone would get blood tests and vital signs collected, and then they would have a PCR test done that would take some time to come back. And we set out in 2020 to see, can we build a model using that tabular data that will give you a COVID prediction even sooner, so that you can have your hospital running smoother, reduce the amount of swabbing and reduce costs. And we initially developed it at Oxford's John Radcliffe Hospital's data, the greatest hospital on earth. But the difficulty with working with data from just one centre like Oxford is that Oxford's population has a certain demographic characteristic and actually biases towards a slightly healthier population that's slightly older and towards a certain demographic, which is, we showed in our data that over 80% of people coming to our emergency department were of a white background. And if we wanted to make models that were fairer, we needed more diverse data, and to do that we needed to collaborate and to reach out to other hospital trusts, in this case Bedford, Birmingham and Portsmouth. And we went on to build a test using XGBoost initially, and we did a pilot deployment of that test in a research setting at the John Radcliffe Hospital and showed that actually we can give you a COVID screening result within 45 minutes using point of care results. Now, the difficulty about all of this is that to achieve that, we had to move the data, and we had to put the data all in Oxford. And that's got limited scalability, it's got privacy considerations that need to be taken into account, which in the context of a pandemic were something that we could discuss. But outside of the context of a pandemic and looking more broadly, of course, the gold standard would be to leave the data where it is. And so we set out to build a platform to repeat that work, but repeat it without moving the data. And we developed a pipeline that was based off of the 2022 edition of Flower and implemented it on Raspberry Pi devices with on Ubuntu desktop so that it was really easy for hospitals to use. And we shipped out these pre-configured Raspberry Pis to hospitals, asked the hospital to plug in a monitor, a keyboard and a mouse, and then you'd log in and you'd be met with a Ubuntu desktop and then an application on the desktop that would kind of walk you through it. And it was designed to be really straightforward, so hospitals only had to upload the data with a USB stick on their premises, and the data would remain on these devices. And we went on to this was our federated setup. So we did, first of all, federated training and then went on to federated evaluation. And for training, we used data from the first pandemic wave in the UK, and evaluation was done using the second pandemic wave in the UK. And we also did an element of site personalization, which I'll talk about if we have a bit of time. And for our data, we had 2 sites that were both training and evaluating. We had one site that was training only, that was Birmingham's hospitals, and we had one site that was a fully held out hospital used as a completely separate evaluation set. So we did an evaluation on the second wave data from Bedford, Bedford's hospitals, as our evaluation set, as well as the second wave of all other sites. And we went on to show these are ROC curves where the blue line is a locally trained model using just one site's data, and the orange line, which I think appears red on the screen, is the federated global model and how that performed at the sites. And as you can see, we get a considerable improvement in the performance of the model on federating it. On average, for the deep neural net that we used, a mean increase in area under curve of 27.6%, and for the logistic regression, slightly smaller but still important mean area under curve of 14%. And the reason that this is particularly important is that populations such as those in Birmingham and in Bedford had more diversity than ours in Oxford, and therefore we hope would bring more fairness to the model, although we didn't formally evaluate that. And these are curves showing how model performance improves over time as we do more and more rounds of federated learning. And what you can see is that you get initially a very large improvement with the first few rounds of federation, and then it begins to plateau or reach a steady state, both for logistic regression models and for deep neural network models. And the final global models that we developed, when validated on a completely unseen data set from a completely unseen hospital, achieved an AU ROC of 0.878 and 0.917 for logistic regression and deep neural net, respectively, and giving you a test sensitivity of 84% and 90% against PCR. So ultimately, very high-performing models that met or meet a reasonably acceptable clinical performance threshold in an unseen evaluation. And the ability to federate this, we hope, will allow us to do this work in future more easily for more clinical indications, and to look at developing tests in the future, particularly in the context of oncology and cancer research. And we published this initial work in Lancet Digital Health last month, talking through some of the challenges that we faced and also the summary of results. Now, thinking to the future, there are some technical aspects that we want to look at and improve, and there are also some essentially clinical questions, so different clinical indications. On the technical side, I'm delighted to see that hyperparameter optimization has come to flower since we did this work, and two improved features in terms of being able to perform pre- and post-hoc sensitivity analyses. And these are things that we sort of really want to look into, because if you find in your training that there is a particular population of interest where characteristics are different, it would be great to be able to explore that post hoc. We want to make this even easier to deploy. We want to make the interface even better. We want to make it more straightforward and more open, and that's something that we'll have further conversations around, and hopefully have more to update in future. And given that all of this code is written using an open framework that is based on the Unix system, it would be quite straightforward for us to implement it on more powerful devices with GPUs, and therefore look at, with of course the features in Flower, look at federated learning with imaging, and excitingly I've just found out possibly language models. And I guess that's everything I had to say on the work. So I want to say a particular thank you to Professor David Clifton at the University of Oxford, who's a professor of clinical machine learning, and Professor Ting Ting Zhu and Professor David Eyre, who are teams that I work very closely with in Oxford. Thank you.
So let's ask Andrew a few questions. Who in the room wants to ask a question? Yeah, we have this guy right here. Pan is going to bring you the microphone. Hold on one sec.
Out of curiosity, and of course if you can answer, what kind of data did you use to train them?
So this is tabular data, so it's your vital signs, which are essentially numerical parameters, and then routinely collected blood tests, the kind of the technical tests, so your full blood count, urea and electrolytes, liver function, and inflammatory markers. And we picked those because actually they're very standardized, so every patient coming through the door, or near enough every patient, will have those collected, and so you've got good data before the pandemic and after the pandemic, so you can develop a very neat classifier. And secondly, because it's structured and it's tabular data, which is collected by a machine and not human entered, you can have quite high confidence in the fidelity of that data.
Yeah, so numerical data, so it should be quite fast, right?
Yes.
Okay. Yeah.
Yes. So even with even using a relatively low power device, the training I think took a total of 3 hours across all of the sites, which is something that's fine. The Raspberry Pi 5, I gather, is twice as fast, so would sort of hopefully help us do more intensive things in future.
Thank you.
We got another question there.
Hi, I'm José Diniz. I'm also a medical doctor doing research on federated learning. I have 2 questions. Regarding data harmonization, did you have any difficulties regarding these 3 parties? And the second one, for the future steps, are you envisioning any work regarding prevention, especially on primary care and out-of-hospital systems, as more and more the burden of disease is related to avoidable, modifiable risk factors? Thank you.
So to start with the question on data harmonization, that is always a big challenge. And we tried to design the setup as well as we could to minimize the risks. And so by using vital signs that are highly standardized and collected in the same way by trained staff every day, day in, day out, and by using data that comes essentially as an automated output from a machine, and the companies that make the machine, actually one company called Sysmex has a monopoly in the UK, and so every hospital taking part had the same brand of machine. We were able to sort of, with reasonable confidence, say this data is going to look in this format from each of the sites. And then we said to the hospitals taking part, we'd like you to only provide data for over 18s. We'd like you to only provide data according to these criteria. And we also put it in the code that we enforce those criteria. So if anything had slipped through the net on their side, the code was set up to sort of throw out under 18s from the analysis. So essentially, it does require either a degree of sort of mutual understanding between you and the hospital taking part, or it requires some knowledge of the data beforehand. And there are sort of ways you can do that. You can look at summary metrics, medians, etc. But it is something that needs careful thought. The second question on prevention, I think, is an important and pertinent one. I guess as a hospital doctor, the stage to look at prevention often is before you come to hospital, and that perhaps might be something that is sort of more thoroughly explored by colleagues in primary care. The data sets are different and the data locations are different. Every hospital has its own database, and actually every GP practice also has its own database, but there is better infrastructure in aggregating that. And there are already large pan-UK databases to access primary care data. So that could be, in that setting, the value out of federated learning is perhaps a little bit different. It might be aggregating primary and secondary care data rather than necessarily to try and access data in several general practices where each practice will only have a few thousand patients.
I think Charles has a question from Slack.
Yes, there are a few. One of them is whether or not privacy-preserving methods were used during the experiment, and if not, was it okay to risk leaking this data?
So on privacy preservation, I think we took what we call in medicine the Swiss cheese model, where you look at applying multiple different techniques on top of each other, so that if any individual technique fails, you'll still be all right. And so, for example, all data pre-analysis was redacted by the hospital before being put onto the Raspberry Pis. We didn't handle any identifiers with federated learning, so we only used your vital signs and blood tests, which, if leaked, are relatively meaningless anyway. We used SSL encryption, which is built into Flower. And so ultimately the models as well we were using had relatively few parameters. They were quite simple 3-layer deep neural nets, and not, for example, a 1 million parameter adapter or a language model. And because the size of the data was so much greater than the number of parameters you have, again, the risk for leakage is lower. So we hoped that by using a combination of different techniques to mitigate risk and ultimately data that isn't particularly sort of sensitive, that we could get around that.
Thank you. Another one is about the hardware limitations of the Raspberry Pis, if you can maybe elaborate on what kind of
Yes. So for this tabular data task, the Raspberry Pi was more than adequate to do that job. Now, the hardware has to match the task. The reason we use the Raspberry Pi is because you can pull the SD card out from the bottom at the end of it and physically destroy it, which for hospitals gives you a bit of confidence that your data is secure when you've finished. It's also very cheap, and so we could give them to the hospitals and not want it back or not require it back. And because it's cheap and because the SD cards are clonable, it's quite easy to scale that up to, say, 50 hospitals or 100 hospitals in a way that you couldn't with more expensive hardware, or that perhaps might take a bit longer and a bit more money with expensive hardware. So here, the hardware was adequate for task. If we're looking at federated medical imaging with CTs, then of course we need GPUs, and language modeling, of course, we need GPUs. So it's sort of meeting your task.
Thank you.
Okay, so let's thank Andrew again. Thanks very much, Andrew. So let me just check one thing. Our next talk is a remote talk given by Hui Gran. Is she there? She's there. Perfect. Okay, because we're running very slightly ahead of schedule, but that's actually perfect. So let me introduce. Let me introduce Hui. She is really a rising star in the area of machine learning and systems. She is an assistant professor in the College of Information and Computer Science at the University of Massachusetts Amherst. And she received her PhD from North Carolina State. And at Amherst, she leads a group that investigates these boundary topics between machine learning and systems. The reason why we invited Hui was that we realized that her group has been very productive in the last 12 months and has frequently used Flower to produce top-tier machine learning publications. So she and her team has invented methods called Flow and Flash as two examples of things that they've produced that appeared at ICML and iClear. And then to do this research, they use Flower. And so for that reason, we wanted to invite her to attend. Unfortunately, she couldn't make it here physically, but we really wanted to hear where she was going next with this line of work and where she generally thought the space of federated learning was taking us. And so we wanted to invite her. So that is an introduction. I really want to thank Hui for being here and talking to us all. Thank you very much for joining us today.
Well, I suppose this is the time I take over.
Yes, please.
Yes. Okay. Yeah. So I do hope that I can physically visit London, but yeah, we will do next time. So this work is done by my amazing PhD student, Kunjo. You can see her picture here too. I hope I also look exactly as the picture several years ago. So Kunjo was also here to make sure that I'm going to do a great job explaining the work. So before I start to present the work, because the work itself uses the setting of cross-device federated learning. So let me first refresh this concept for you. In the cross-device federated learning, you have a server, and the server hosts a global model, and you also have a set of clients. And these clients are willing to do all the hard work of training a machine learning model because they do not like to share their data to the server. And in one round of federated learning training, server will send the global model to a few selected clients, and clients will train the global model and then send the updated global model parameters to the server. The server do the aggregation of the model and prepare for the next round. So there are some general assumptions in cross-device federated learning. For example, you can assume that even though you will have a lot of clients, but only a fraction of the clients is going to be available for training the models. And each of the clients are likely to take part only once or a few times, and they may not like to actually store some of the states. You also have very limited sample counts on each of the device or each of the clients. So that's roughly about 50 to 400 amounts of data. And now let's look at the number one enemy for cross-device federated learning, that is data heterogeneity. Assume that the blue dot represents a global model from a previous federated learning round. And then after a client updates the model, the new model is represented in the green circle. If the data are homogeneous across clients, then the other clients would move the global model in a kind of similar way. And then after the server do the aggregation, the global model, that is the yellow circle, that will make everyone happy. However, when the data are actually heterogeneous across clients, some of the clients who are more unique will not really benefit from the aggregated model and thus has a very worse performance. The data heterogeneity issue can even change across time. Suppose each of the clients has their current local data and they work hard to make sure that the model converge. However, the local data on the clients could change over time. Then gradually, some of the clients that has very different local data would also suffer from the poor model performance. So we call this the concept drift in the client. In this talk, we're going to introduce two of our recent work. One tackled the problem of data heterogeneity across client, and the other one is to further consider data heterogeneity across time. Specifically for Flow, we introduce per instance personalization and can boost the accuracy of the clients by up to 4.5 times %. And then the other work, Flash, which propose a server-side drift-aware optimizer, and it can achieve faster drift recovery. So let's start with the first one. So manual work has been proposed to handle cross-client data heterogeneity, and the way it works is to personalize the global model for each of the client. So Flow is motivated by the limited performance improvement from existing approach. So what we observe is that not all the clients can benefit from personalization. So the plot we show here show the x-axis are different personalization methods. The y-axis are the number of clients who do not benefit from the personalization. That means the personalized model actually achieve worse accuracy compared with the global model. We can see that up to 30% of the participating clients can see a performance drop even after personalization. But with Flow, we can decrease this percentage of harmed clients to 7% for this particular data set. And then another motivation is if we notice that even for the clients who do benefit from personalized model, not all the instance that sits on that client actually prefer a personalized model. So again, in this figure, the x-axis shows the personalization measure, the y-axis shows the percentage of the instance that can be correctly classified by both personalized model and also the global model, or only the global model or only the personalized model. So with Flow, we are able to actually boost the number of clients for all the categories and decrease the number of clients that benefits for only global model. So our goal in Flow is to try to get a personalized model which can process each of the instance and then let it propagate through either the global or the local model layers, depending on which layer is expected to fit the instance better to overcome the aforementioned issues. So this is achieved by a policy model which acts as the decision maker for each of the instance to pick between the global and the local parameters. If we expand even further, we have this policy module is divided by base and exit module. The base module will take the instance as the input and then output intermediate representation for early exit and attached to the base policy module. The exit corresponding to the layers of the global and the local model. So we derive this local model by doing the fine-tuning of the global model, and then we start to do the training of the policy and also the global model parameters alternatively so that we can dynamically route each of the instance on the client. We show some of the results here. It's using LSTM, which is a recurrent neural network on Shakespeare for next character recognition, next character prediction. And the x-axis shows the Federated Learning rounds, and the y-axis shows the validation accuracy on each of the client. We can see that Flow can achieve much higher personalized accuracy over the best performing baselines. And if we further look at the behavior of the routing decisions for each of the instance on a client, we can see that they actually fall into three categories. That is, the instance preferred or routed to only the global model layers, or the instance routed to only the personalized model layers, or both of them. So we realize that for the instance that do prefer to get classified using the global model, the routing parameters are more likely to pick the global routes, shown as the yellow. And then if the instance prefers the personalized model, the routing parameters do pick the local model routes more likely. And then for instance that can be classified by both, then the routing policy still prefers the global model because of our training mechanism. So the main takeaway from this first work is per instance personalization can help improve the data, improve the performance of the model under data heterogeneity. And then the main insight is to have a dynamic personalized model instead of our static ones. And then it can help improve the accuracy on the clients by up to 4.6%. So The previous work has been looking at what kind of models that a client side can train in order to handle data heterogeneity. In the second work, we look at how can the server side help with the data heterogeneity, and particularly how can the server side help with the concept drift combined with data heterogeneity. So just to address heterogeneity across clients, there has been some work proposing adaptive optimization that can be done on the server side to address data heterogeneity issues. The way it works is you have these gradients, and you keep track of the gradients statistics, and so if we use the delta t to represent the gradients, and then it will keep track of our second momentum of these gradients, as denoted as a VT in this equation. And then to update the model parameters in the global model, we use the previous model weights and then plus the first momentum and then scaled with an effective learning rate. So this effective learning rate is, it has a learning rate and then divided by the square root of the second momentum. And then we get a new updated model weights. So this is typically how adaptive optimizer work. So, but we realize that although adaptive optimizer are very effective in handle data heterogeneity across client, but it can be very slow to adapt to the drift that is across time heterogeneity. The plot below shows the accuracy curve during federated learning, and at the onset of a drift, an existing approach, FedYugi, that is adaptive optimizer, can take a while to recover from the drift. So that is a FedYugi, and the H is the yellow curve. And then if we do not use adaptive optimizer, the performance is going to be even worse. That is the purple line. So that is the Fed average. And you can see that even without drift, the accuracy is by no means that is as comparable as accuracy from adaptive optimizer. So the lesson is adaptive optimizer do help with data heterogeneity, but it is very limited in handling concept drift. So we find the reason that adaptive optimizer cannot actually adapt to the drift fast is because its effective learning rate is relatively small, even when the drift happens. So Flash instead tries to increase or try to modulate this term, and so that we can make it drift aware, such that when a drift is detected, effective learning rate can increase so that we can accelerate drift adaptation. The core insight in Flash is we find that the difference between the squared gradients and the second momentum of the gradients aligns very well with the drifts. So we call this a gradient disparity. The plot on the left shows how gradient disparity will change with the number of rounds in federated learning, and also how does it change if the drift start to happen. So without drift, the gradient disparity becomes smaller and smaller as the training converges. However, when there are drift happen, the gradient disparity goes up. So our basic idea is to use this gradient disparity to modulate effective learning rate. And the way it works is this. So we keep track of the gradient disparities. On the server side, we keep track of these gradient disparities by doing a moving average. So then we get this B term. And then we compute the drift-aware effective learning rate by adding this moving average of the gradient disparity term, so that to achieve adaptivity. And then we assume that if the gradient disparity is going to be higher because of our drift happen, we can get a higher moving average. Because of the higher moving average, the drift-aware effective learning rate is going to be higher as well. And because of the higher learning rate, the client side can train the model so that it can adapt to the drift much faster. The main result I show here is for incremental drift. So in incremental drift, we assume that like 20% of the clients will change their data distribution every 100 runs, starting at runs 2000. And we also showed so the x-axis are the number of the runs, and the y-axis are the validation accuracy on each of the clients, and different curve corresponding to different federated learning algorithm. We show that, so the purple one is the oracle. That means you have perfect knowledge on when the drift will happen. The blue line shows the flash. So we show that the flash can enable much faster recovery compared to the baselines. And also flash also has a chance to achieve higher accuracy even after the drift happened. The main takeaway from the work is we can use a server-side drift-aware adaptive optimizer to help combat with both data heterogeneity across device and also data heterogeneity across time. By keeping track of the gradient disparity, we can try to balance the stable training without drift or even with drift. So Flash are able to recover from our drift very quickly in roughly 60 rounds of federated learning training and achieve the least percentage of accuracy drop compared to the Oracle. So I'm very proud to say that all the work are built with flowers. And if you have any questions, this is the time to ask. Thank you very much.
So do we have questions in the room? We have one question down here. Payne will be there with you momentarily.
Hello, do you hear me?
Yes.
Great. So thank you very much for the presentation. It's pretty nice. I would like to know if this flash concept that you are introducing, have you done simulations to check if it works under any level of concept drift? Like you were mentioning that you were doing something like close to 20% that it changes, but have you done more, let's say, simulations to check that it works under any level of concept drift?
Yes, so we have very extensive evaluations in the paper. We consider incremental drift, we consider sudden drift, we also considered like a recurrent drift, and then we consider different percentage of clients to have drift in the incremental setting as well. We show that Flash can give you the best performance in all those settings. We even considered even without drift at all, and Flash can give comparable accuracy with existing adaptive optimizer.
Okay, thank you.
Great. Any more questions here? How about online? Oh, sorry. Yes, there's a question just at the front. Thanks, Pan.
Hello. So my question is that, so the data can be heterogeneous across the clients because of different regions. And one of the region can be a dishonest client. So if a couple of dishonest clients are present, they will have a heterogeneous data. And so maybe my question is that how the global model will be impacted when we have a dishonest client?
So I didn't quite get the last sentence. So what will happen to the global model if a client has what?
Yeah, so how the accuracy of the global model will be impacted if we have a couple of dishonest clients having heterogeneous data?
Okay, so that is what will the performance of the global model if only a very small percentage of the clients has heterogeneous data? Is that the correct understanding of the question?
Yeah, a very small percentage of the clients are having heterogeneous data, but we do not know whether these clients are dishonest or they're having really out of distributed data.
Oh, I see your point. So I mean the clients who have decided. who have heterogeneous data could be they're not honest at all, or it could be even that they get under attack. So I think that's part of the benefits of doing personalization for the client. In this particular work, we didn't actually evaluate for adversarial or attack setting. So the goal of this work, the goal of the flow, is to make sure that the global model is get trained in a way such that after it get personalized for each of the clients, they can get good performance on each of the clients. So all the clients has data sets that are different from each other. So you can think that all the clients in a way, you can think all the clients are dishonest. So all of their data distributions are different. In particular, we do the simulation with, in this particular example, we are using, so in this particular figure I shows, it uses a LSTM model and then try to do next word prediction. And we use the ready data set. So the ready data set, it's already inherently heterogeneous, so that every single client will have a different set of data sets and their distributions are actually different. So does that answer your question at all?
Sure, that's fine.
Yeah, he's nodding. I'm sorry, it's a little bit difficult when you're remote and you don't have a camera. I'm sorry for that. Charles, nothing? Well, actually, we're bang on time, so I'm going to close it here. And thanks again so much, Hui, for telling us about these two fantastic pieces of work. Thank you. Thanks so much. So we are now going to run the poster session. And so the way the posters are going to work is that after the session we're about to have, there'll be a break. The break will last for about 30 minutes. And at that time, you can get snacks, but you can also visit a variety of posters that are in this building. There's about 5 or 6 of them in this room. There's a number of them downstairs. There is food up in this room and food downstairs. And so the way we're going to tell you about these various posters is by doing a 1-minute poster pitch. And so I'm going to read out a few names. It's a subset of the posters who decide to want to participate in this session. So if I read your name out, come up to the side just down here, and then we'll show your one slider one by one. So just come down. So please come down immediately, though, when I read out the names. So there's Sergio from High Ibra. There's Dennis from TU Berlin. There's Steve from Duke Kuan University. There's Philip from TU Berlin. There's Yong Guan Kim from Gaocheon. There's Francisco from Newton. There's Lorenzo from Messina. There's Jose from Health Data Science, and Dimitri from Genext. So those are the groups of people who are going to give this pitch, this 1-minute pitch. You'll hear about the poster, and we'll be doing more pitching next day. But so in the order that I read the names, feel free to come up, and you'll get your 1 minute. Yeah. So feel free to start.
Yes. Okay.
Time starts now.
Okay. Thank you. So good afternoon, everyone, and welcome to the Future of Sustainable Mobility. Today I have the honor of presenting GREEN. The GREEN project appears as a solution for the mobility sector. It utilizes 3 key technologies, Federated Learning, blockchain, and smart contracts. The focus of the project GREEN is to optimize the charging environment for the electric vehicles. The project is focused on the project objective is to enhance the charging infrastructure to promote the electric vehicle adoption and to reduce pollution. So how do we do this? We federate the local models in each state charging station, enabling the collaboration between the charging station managers. And we also create a network with blockchain and smart contract for a decentralized and secure network. Sorry, my time is just 1 minute. Sorry, 1 moment. I'm sorry. So to decentralize and to share the data. It's also important. It's also important to make use of the artificial intelligence models, which are physics-informed machine learning, that also help us to enhance to get more precision and efficiency in the models. So
amazing. Thank you. Thanks so much. Perfect. Again, that was Sergio Zara Mata from High Ibra. Great stuff. Next, we have Dennis Greenwald, TU Berlin.
Hi, everyone. My name is Dennis. I'm a PhD student with the Machine Learning Group at TU Berlin. And today I'm going to present a work that we developed for tackling the problem of personalized as well as global federated learning at the same time with very low overhead. And how we do that is that instead of training a single model, with a single set of weights, we train a whole space of models that has a really simple parameterization. In this case, it's parameterized by the simplex that you can see, this triangle over there, where we have basically 3 model endpoints. And we want to train these model endpoints in such a way, and we can sample between these model endpoints any point in the simplex, and we would want to train them in such a way that different regions within the simplex specialize to different data distributions. And by doing that, having a trained simplex like this, we can assign personalized models to each client that work really well as having an ensemble or a single model that performs well on the global test distribution. We've benchmarked this against several benchmarks on several different non-IID splits. Thank you.
Next, we have Steve Hay. He is a system programmer at Duke Kushan University.
Thank you. Hello there, Steven here. I developed FedKit for Federated Learning in Fed Campus. The main goals are train and aggregate the same machine learning models across Android and iOS, avoid app updates for model changes, and separate software developers and data scientists' duties. For the first part, I developed a cross-platform model pipeline to convert models written in Python and train them using TensorFlow Lite and Core ML and aggregate them using Flower. This pipeline also separates the duties of model development and deployment, addressing the third issue. I developed machine learning operations, ML ops, by embedding Flower servers with Django web server. Check out our poster. Thank you.
Next, we have Philip Weisner, Research Associate, TU Berlin.
Yeah, hi everyone, I'm Philip. You can find my poster downstairs. So during my PhD, I've been researching on how we can better align the power consumption of distributed computing systems with the availability of clean energy. And you can guess that federated learning is a good use case for that. So through client selection and determining how much work clients are supposed to do, we can maybe reduce the carbon footprint of federated learning. And you can guess that it's probably quite hard to test such systems because we do not have globally distributed energy system test beds. So we came up with a co-simulation framework that we've been developing for the last 1.5 years, and we're presenting here. It's called VESIM, and it basically allows your federated learning clients, no matter if they're like real or simulated, to interact with a simulated energy system. Yeah, that's it. Thanks a lot.
Amazing. The next I have is Young Gwon Kim, Gaocheon University.
Hello, I'm from Gaocheon University. We are make the FedOps scenario, the software as a medical device, and we are using the vital signs, and we make the FL framework that FedOps we are making, and do the FL application for the critical care classifier. And in this situation, we are making the LMECS algorithm we made for the client selection algorithms. At the first floor, our poster is on there. So please come there and see our FedOps. Yes, thank you.
Thank you. There's Francisco Pace, lead AI researcher, Newtwin.
So, hi everyone, my name is Francesco Pase, and this is my last PhD paper, actually. And the idea here is to tackle communication efficiency in federated learning, and models are becoming huge, and they contain a lot of redundant information. And many compression or quantization techniques usually rely on some stochastic computation. So the idea is to represent the model updates, and instead of deterministic values, as optimized probability distribution, like QK from client K and P from the server. So P is the global model distribution the server knows, and every client knows at each round. And the idea is how can we send those updated distribution with some samples. And so we use the information theoretic concept of communicating samples from the client to the server, and we develop KLMS, that is scale minimization with side information, that is coded and compression blocks that can be applied on top of many existing training strategy to compress models and reduce the rate to the K divergence between Q and P. And with KLMS, we can optimize and we can improve the communication accuracy bitrate trade-off, as you can see here on the bottom right. Thank you very much.
Next, we have Lorenzo Carnevale of the University of Messina. He is an assistant professor there.
Yeah. Good morning, everybody. I'm Lorenzo Carnevale. I come from a distributed system groups, and we have been called to work with robotics and deal with ROS, the robot operating system. The main problem is ROS uses data distribution system communication paradigm, which is based on publish-subscribe. That means we couldn't use any federated learning framework as it is. So that's why we built FedROS with the aim to be a platform as a service, cloud computing model. So we implement a YAML manifest to submit jobs, federated learning jobs, with other parameters, model, optimizer, loss function, and so on. And we had to deal with two main issues. One is that ROS needs to be built. So that means we need to build training and aggregation, so the client and the server. And the interface message needs to be defined before of the building. So that means we need to compose the client and the server before of running the jobs. So we try to make some performance in terms of composing. And then, we have the poster just over there and the demo to show you up. Thank you.
So we have Jose Miguel Diniz. He is a PhD candidate, health data science.
Hi, hello everyone. So as it was mentioned before, there are a lot of examples of health data being segmented across multiple people or organizations or functions. So my work focused on the state-of-the-art of federated learning and comparing it with either centralized or local-only models. And I have a few articles from Andrew on my systematic literature review. What we do is that we map different clinical applications, different diseases, and we extracted a lot of data of the different comparisons and parameters and kind of performance tests to make a good synthesis of what's going on and how to convince decision makers and policy makers to adopt FL in the future. So just a quick interesting fact, federated learning comparisons were better than local models more than 80% of the time, and in almost 20% of the time they were better than their centralized counterparts. Thank you.
So our last poster presentation is going to be done without a slide. We have Dimitri. He is a data scientist at GeneXt, and so over to him.
Hi, I'm Dmitry Kolobkov. I'm going to present a poster called Federated Learning for Data Collaboration in Genomics. Healthcare in general and genomics in particular benefit from utilizing multiple data sets to train a single model. However, in case of genomics, the use of federated learning is under-investigated, and in our recently published paper, we we investigate it and see, we first show on the UK biobank data set split into multiple nodes the efficacy of federated learning, and then we investigate what happens if the clients are heterogeneous. Please come see my poster downstairs.
Amazing, thank you. So for those who are online, what we have done for you is produce videos of all the posters, and you'll start to see those posters during the break. For those folks who are here, we're going to have a half-an-hour break. There's food in this room and drinks in this room and the room downstairs, and you can see all the posters you just heard from and others as well during the break. So enjoy the time. You'll see a countdown timer. After 30 minutes, we'll return back for session 2. Thank you very much for session 1.
Hey everyone, my name is Daniel Jimenez and I want to show you our recharged version of FedRML, which now includes feature and quantity skew parts together with their quantification methods. In a previous video from the Flower model that you can find on the YouTube channel, we mentioned that Tony Stark's greatest invention was Jarvis, his AI tool that helps him to solve problems in an easy, controlled, and quickly way. Thus, our greatest invention so far is FedRML, which permits the creation of federated datasets from centralized ones, controlling the level of non-IIDness, and now we have included feature and quantity skew partitions in our library. We have defined formally what we meant by a centralized dataset and distributed or federated datasets. And from there, we formally define label and feature skew distributions, which took to the definition of label skew, feature skew, and quantity skew. And finally, we have introduced Jensen-Shannon distance and Hellier distance to quantify the level of non-IIDness in federated learning. Now let's see what are the new attributes that we have included in FedRML, and let's start from the feature skew. We have included the state-of-the-art Gaussian noise method, which introduces a defined level of noise to the features of the clients. Notice that this method has a drawback when sigma is too large, since the model's performance decreases drastically. To solve the issue of the previous technique, we implemented a brand new method called hist-Dirichlet, which creates a histogram based on the average value of the features and assigns each example to a bin. From there, we just apply the Dirichlet distribution with a defined alpha to obtain the distribution of each client. Using our library, Flower, and the FissionNet 2020 dataset, we made a comparison between the Gaussian noise and the hist-Dirichlet method, showing that with our new method, we do not damage the performance of the model, and also that high levels of feature skew do not decrease the results of the model. Now, regarding quantity skew, in our library, we implemented the state-of-the-art method based on the Dirichlet distribution using the desired alpha. However, this method cannot be used when the data is too small or the number of clients is too big. Then, as a solution, we propose the min-size Dirichlet-based method that defines a required minimum size that we want for the clients. And from there, we define the min size as the minimum required size divided by the number of examples. If the proportions are already calculated for each client using the Dirichlet distribution are smaller than our calculated min size, we set that proportion equal to the value of min size. Finally, we normalize the obtained proportions between 0 and 1. Using FedRML and Flower, we split our FissionNet dataset based on the quantity skew, determining that the federated and centralized model have very similar performance, even increasing the level of non-IIDness. So we can conclude that the Jensen-Shannon and Hellier distances are appropriate for quantifying the degree of non-IIDness of label, features, and quantity distribution among clients. Second, FedRML produces federated datasets starting from centralized data, facilitating a comparison of centralized and federated learning. Thus, as a consequence, the datasets are consistent and generated with a measurable level of heterogeneity. We are including methods to measure and simulate scenarios with a spatial temporal skew to have a more efficient version of our Jarvis. And we are using our tool to conduct a systematic and controlled comparison of aggregation algorithms such as FedProx, Moon, FedYogi, FedAdam, and all those baseline implemented in Flower. Here you can find some of the references that we employed in the construction of FedRML. And that's it. This was a fast journey over our tool that we expect will be helpful for the future research path that we will continue. And of course, we hope that plenty of researchers will find it a great assistant. Please scan the QR code, play with the library, and let us know if we can do anything better.
Hi, my name is Dennis Greenwald, and I'm a PhD student with the Machine Learning Group at the Technical University of Berlin and the Berlin Institute for the Foundations of Learning and Data, or in short, BIFOLD. And today I want to speak about our recent work on subspace training for federated learning. In our work, we consider the problem of statistical heterogeneity. This can be briefly grouped into the four following groups. We have label distribution skew, that is, the label distributions between clients might differ. Then we have the feature distribution skew, where the input features between clients might differ. For example, client 1 might draw his or her zeros differently than client 2. Then we have the quality skew, where some clients might exhibit noisy data points. And we have the quantity skew, where, for example, some clients that are represented by big enterprises have a large amount of data points, whereas other clients that might be represented by edge devices have a comparable small amount of data points. Neural network subspace learning, instead of training a single model until it converges to some local minima, in subspace learning, we tried to train a higher dimensional simplices. For example, a one simplex that is represented by the line that connects two different random initializations of the same model. And we want to train this line in such a way that each point that we sample that lies on this line exhibits a low loss on our training data set. And we can do so by minimizing the following double expectation. So for each mini batch XY out of our training data set, we sample an alpha. Alpha corresponds to a point on the line, either uniformly or we can pick some other distribution. And then we want to minimize the loss on this mini batch using the alpha model that we've just sampled. And the loss might correspond to cross entropy, for example. And what we end up with is such a line where the midpoint of the line actually outperforms standard training in terms of accuracy, calibration, and robustness. And now, of course, since we have a whole space of models, we can sample multiple models to make a prediction and ensemble the predictions. For the case of a two simplex, this would correspond to such a triangle that is spanned by three different random initializations, for example, and we can minimize any point that lies inside of this triangle. In our case, we want to use subspace learning for federated learning in such a way that we group clients to different groups or different regions within the simplex. And the groups of clients are determined by their data distributions. So now clients that have similar data distributions should end up in the same regions of the simplex and sample models from this region. In this case, we grouped our clients into 5 clusters, and each client now gets assigned either the midpoint of such a cluster region or any other point that we can sample from this region. And what we show is that this yields improved personalized models for each client. And since we have a whole simplex of models, we can also sample either the midpoint of the whole simplex or an ensemble of models that fits the global test distribution really well. So in our case, we have tackled two problems of one, the problem of having a personalized model for each client and the well-performing global model for the global test data set. Our method works the following way. First, of course, we need to define which client statistics we will use for clustering. Then we will project these client statistics into our simplex that we train. And in our case, we project it using latent Dirichlet allocation. Then, given a certain distance function, we, of course, have to cluster within the simplex. We use Hilbert simplex clustering for it. And once we have determined our cluster centers and the cluster regions, so every point within the simplex that belongs to a certain cluster center, we can, after projecting a new client, assign to this client either the cluster center for inference, or during training, sample multiple models uniformly, for example, out of this cluster region in order to train our simplex. We have evaluated our method against several baselines on several different non-IID splits. So here we have the 2-fold split, 5-fold split, and different Dirichlet splits. For the 2-fold and 5-fold models, we can see that SOSIC and SOSIC FL+, which are our methods, strongly improve the baseline performance. For the Dirichlet, we also see an improvement of performance. So to conclude is that solution simplex learning allows to increase personalized and global performance at the same time, as we have seen. And we can apply our method actually both on randomly initialized as well as pre-trained models, where we just train the simplex over the last classification layer. For future work, we want to cluster our clients based on different statistics. We want to employ optimized ensembling techniques, and we want to apply it to continual federated learning. Thank you for listening.
Hi, my name is Dmitry Kolobkov. I'm going to talk about how federated learning enables data collaborations in genomics. While the use of federated learning in healthcare and genomics in particular looks very promising, it has been poorly investigated. Our team at Genext has recently published the first study that explores the efficacy of federated learning in application to large-scale genomic data. Let's start with a short introduction about genomic data and what we can predict from it. Genomic data is the information contained in our DNA. Our genome contains a lot of valuable data that, for example, helps us invent new drugs. The most direct use of genomic data in machine learning is to predict a phenotype. A phenotype, such as an illness, is an observable effect of the interaction of individual's genome with the environment. The goal of predicting phenotype from genomic data is to identify individuals more susceptible to a certain disease due to their genetics. These individuals can be monitored more closely to detect the disease at an early stage. In individuals of different genetic ancestries, phenotype can depend on different genetic variants, which means that phenotype predicting models trained on one population can poorly perform when tested on another population. The majority of genetic data comes from individuals of European descent, which means that models trained on this data perform poorly on individuals of other ancestries, which increases disparity in healthcare. Training a single model on multiple genomic data sets from different populations reduces this bias and makes phenotype from genotype predictive models more fair. On top of that, combining genomic data sets increases sample size, which leads to more accurate models. Increased sample size also boosts statistical power, which allows us to add rare variants as additional features into the model and to predict rare diseases. Genomic data, however, is extremely sensitive, and its leakage may lead to serious consequences. Due to this fact, data custodians may not allow moving and merging genomic data, which means we cannot pool all of the data sets together at a single location and train a model. This creates an ideal scenario for federated learning. In order to investigate the efficacy of federated models on genomic data, we considered the UK Biobank dataset, which contains genomic and phenotypic data for more than 350,000 individuals. We split the UK Biobank dataset into 19 isolated nodes according to data collection centers and trained models predicting 8 continuous phenotypes. We then trained centralized models on all data together, federated models on all nodes in federation, and local models on a single node with 2 types of data per processing. The y-axis of the graph shows R² for observed versus predicted phenotype, reflecting model performance. The x-axis shows 6 of 19 local nodes sorted in increasing sample size and federated and centralized data. We can see here that for all 8 phenotypes tested, federated models showed in green performed almost as well as centralized models in blue and consistently outperformed 2 types of local models shown in purple and orange. This suggests that federated learning can be used to successfully establish a collaboration between multiple genomic datasets to predict clinically relevant phenotypes such as diseases. Finally, to mimic the scenario where collaborating datasets are drawn from different populations, we investigated the performance of federated models in the presence of high internode heterogeneity, or client dissimilarity in federated learning terms. We split the 1,000 genomes dataset containing genomes of 26 human populations into 5 modes according to sample superpopulation. Here on the graph, we see the performance of federated average strategy with different number of epochs in a communication round. This shows that using more frequent communication between central server and the clients drastically increases the convergence speed by tackling client drift. Thank you for your time.
Hello, my name is Yonggyun, and I come from Gachon University. Today, I'll present about our FEDO 3D silo solution. This is our scenario. First, each has to collect patient data from the emergency room and from the ready state set. Next, each hospital performs federated learning using FEDOS, our FL framework. The results of the execution appear as FL application. Our application is a critical care classifier. The application tells you how to respond in the emergency room depending on the patient's severity. The dataset we used in the scenario is Redis dataset, and this is emergency room patient information collected from 172 hospitals. 100 hospitals randomly selected as clients were set as training, and the remaining 72 hospitals were set as tests. We conducted an experiment comparing centralized learning and federated learning, and an experiment comparing the results of only local training and federated learning. As a result, centralized learning showed the highest performance, and an important indicator in the 3D model is AUC, where over 80% is considered as a good model, but federated learning showed the performance below the 80%. So to solve this problem, we created an algorithm called LMECS. LMECS is an algorithm that selects clients by evaluating the performance of the local model. It is an algorithm that first scores the client and then select only those clients whose scores are higher than the score set by the user. This is the source code we wrote, and we implement like this to the FL. And as a result of LMECS, the overall performance was very similar to centralized learning, and the AUC also increased to over 80%. So you can also see that the execution time has been greatly shortened. Lastly, let me tell you about our plan based on these results. We plan to create a dynamic adaptive client selection feeder and apply it to FedOps. This is a feeder that automatically selects clients based on the local model performance and client's resource. We will use this to enable users to create models that are easy and perform well. My presentation is ended, so thank you for listening.
According to a recent study, the Fortune 500 manufacturers lose a staggering $1.5 trillion per year due to unplanned downtime. Because of that, predictive maintenance is a key element when it comes to the overall maintenance strategy. Predictive maintenance can roughly be categorized into two kind of models. There's the physical-based model, where based on the physical understanding, you come up with a mathematical description. And then there's the data-driven models, where based on empirical incidences, you try to predict future events. We discovered a hybrid approach where we created a mathematical foundation that can be applied to PID controllers. PID controllers are a feedback loop system. They are applied to vast areas in the industrial setting, from the controlling of temperature in thermal components to motion controlling of robotics. Now, the PID is the result of a linear equation where gains are multiplied with the different components of the PID, the proportional, the integral, and the derivative. These gains we can compute. We can use 3 consecutive equations of the PID, and then we have a linear system which we can use to compute the gains. We can compute these gains and then make statements about the system, whether it's working or not. And because these gains don't contain any information about the processing, we can actually centralize these gains using a federated learning approach. And then in the centralized system, we can compare gains of countless machines with each other and then find anomalies. This anomaly detection allows us to find components that aren't working the way they're supposed to. In practice, we have access to over 400 machines, and we are able to analyze the heater band, which is a thermal component of machines. Now, in general, what we've seen is pretty much what we'd expect. The gain values of the PID controlling the thermal element are configured at the installation phase of the machine, and afterwards they're rarely changed. So in general, we have a normal behavior where, given some noise in the data, the computed gain oscillates around the true value, the actual gain. There are, however, some components that we detected through this anomaly approach where we have an increase of the gain for the integral, and then all of a sudden all gains together drop drastically. And actually, when we analyzed that, we realized that the component has actually failed. We also realized another behavior where, in general, all the gains start to behave very erratic. In that case, there was actually a processing issue. This is a perfect example on how, through this analysis, we're able to detect issues with other components, processing issues, not just for the component that the PID is actually controlling. Applying this analysis to a large scale of real-world data made us confident that this can be an essential future approach for predictive maintenance.
I'll start. Okay, let's take our seats here. We're about to start session 2. Okay. It's an exciting session. It's worth sitting down for. Yeah. So we'll grab a few people from out in the other room, and we can start things. Yeah. Okay. Great. Let's give it a couple of minutes for people to settle down, and we can get things started. Okay. So we're going to start session 2 by starting to examine some other important next steps for Flower. We're going to consider how Flower can work with the community through a series of initiatives. We're going to discuss some of the initiatives that have been successful in the past and some of the initiatives that we're going to push forward in the future. And to do that, we've got 2 fantastic research scientists from Flower Labs, Javier and Jan. I'm going to hand over to Javier first, and we can get the session underway. So over to Javier.
Thank you, Nick. So in the next 5 minutes, I'm going to tell you about some of the amazing community initiatives we have been running over the last few months. But first, I want to draw the attention to you, the Flower community. I think we have grown a lot in the last year alone. For example, the number of open source projects that are available currently in GitHub has risen by over 60%, and some of them are quite transformative, like, for example, the FL4 Health project that you will hear more about from the from the Vector Institute in Canada. The number of contributors has also increased by more than double, and some of you have been helping us to improve the core framework. Others have been working on examples, others improving the documentation and creating new tutorials. And another dimension where we see our community really thriving is in platforms like our Slack workspace, where we are more than 3,000 people using Flower or interested in federated learning in general. And we expect that we will see all these kind of super nice interactions and even more interesting ones in our recently launched Discuss forum. And because of this, it's not a surprise that now most of the latest and greatest research in federated learning is created using Flower. You heard about some of them in the previous talks. There are quite a few papers presented in NeurIPS, ICLR, ICML, and the top computer vision conferences. And this is a trend that we started noticing earlier last year, and that motivated us to launch our biggest initiative so far, which we called the Summer of Reproducibility. So for those of you that were not in the Flower Summit last year, we launched this initiative to address a crisis, the crisis of reproducibility in machine learning, which is particularly pronounced in federated learning. Because as you know, while reproducibility in machine learning is difficult because you have models, how you initialize the model, hyperparameters, optimizer, and so on, in federated learning, this gets exponentially worse because you introduce a new big range of hyperparameters, like how many clients do I have, how many clients per round, how do I sample the clients. So this makes the reproducibility of experiments, of research, super challenging. So we wanted to address this. What the Summer of Reproducibility ended up being was a six-month community-led effort with a super ambitious goal of constructing the largest collection of FL baselines that anyone could reproduce super easily. The process involved 4 simple stages. You could propose your own baseline, the paper you wanted to reproduce, or you could pick one from a list that we created. Then you will fork the repo, open a PR, and then start writing your baseline, trying to reproduce the experiments you chose from the paper. And for the most part, you will be interacting with me, and I help some of you more. Some of you didn't need any help to complete the baseline successfully. After a bit of back and forth on GitHub, most of you managed to complete the baseline. I ran all the experiments you proposed, and eventually we merged your baseline. And you also got a really nice reward. We were really amazed by the super great adoption of this initiative that we saw last year when we announced it. And within just a few days, almost 50 of the baselines we proposed were chosen by some of you. Some of you are actually in the room, and I'm sure that many of you are online. So these are the names I put together earlier this morning of all the contributors that managed to finish the Summer of Reproducibility. I'm particularly super proud of all of you putting all the hard effort, so I think we should give a round of applause to all of them. Let me tell you a bit more about the Summer of Reproducibility, the outcome. So 26 contributors completed it. These are all the baselines highlighted in a more intense yellow that you can use right away in Flower. One of the nicest things about the Flower baselines is that they follow the same interface, they follow the same project structure. So for example, in mine, you are very particularly interested on developing FL methods that work with heterogeneous clients, like clients that have different compute capabilities or they are under different communication bandwidths. So you might want to choose techniques like DepthFL or Fjord. These are super popular frameworks in FL. Well, if later on you say you want to do some complex, non-complex optimization using Dasha, you will see that all the time you spend understanding the code in Fjord is also very useful for Dasha because the code structure is identical. The config system is also identical, so making changes to suit your particular experimental setup is super easy. Not everything is about computer vision. We have also baselines that do speech, which is a super interesting dimension and modality for privacy-preserving machine learning. So with this, we are confident that this is the largest collection of FL baselines. If you check other places, like, for example, papers with code, you will find way fewer baselines implemented in a unified framework. And we are super happy with the result. So far, the Summer of Reproducibility has been our biggest community-wide project. And we remain really committed to open source. So that's why we are maintaining these baselines. More baselines are coming. And we are updating all the baselines to Flower Next in the next couple of months. But there is something bigger than the Summer of Reproducibility that we have been working on very hard in the last few months. And to tell you everything about it, here is my colleague, Jan.
Okay, thanks, Javier. Yeah, so as we all know, large language model, the LLM, has got remarkable performance on different tasks and domains. But adoption of LLM federated fine-tuning is lagging behind the other aspects of the LLM-related work. But the LLM federated fine-tuning can simplify the creation of more personalized and domain-specific LLMs that requires the synthesis of data. However, people usually struggle with like building up the LLMs in federated environments due to the fact that the LLM is typically resource-consuming and also a lack of a user-friendly tool to do that. So today marks a turning point. So we're glad to introduce our next Flower community initiative, the LLM Flower Tune, so which makes the federated LLM fine-tuning very easy to do. So what does LLM Flower Tune work? So it basically integrates a bundle of techniques. It includes the Flower dataset. It used to download, partition, and do the pre-processing on the training data. And easy pre-trained LLM adaptation, which is that you can easily choose whatever base model as a starting point for the LLM fine-tuning, for example, the Llama 2 or any other popular pre-trained model. And also we adopt the parameter-efficient fine-tuning, the LoRa technique, and also we use the quantization during training. Additionally, with the Flower simulation engine, we can efficiently make use of the compute resource to do the FL simulation. So all of them come together, which makes the federated LLM fine-tuning that can be done with just a single GPU. And we have released our first example of the LLM Flower fine-tune. And just feel free to try it now if you get your laptop with you. And I think you must have other many ideas to explore on this domain, and also probably want to adapt this to other domain. So here's the thing. We will launch a LLM Flower Tune leaderboard. So in this competition, we will release a series of tasks on different domains with a baseline performed model. So the task includes the general NLP task, the finance, medical, and also coding-related task. So if you believe your model can beat the baseline model, so we just invite you to immediately submit your code and the model to get into the leaderboard. So now let's see an example of the general NLP task. So we benchmarked 8 models here, and you can see it's on the Alpaca GPT-4 dataset, and you can see the training loss shows a healthy dropping lines on all settings. And as for the VRAM cost, you can see that the 22 GB is enough to train the biggest model, and the smallest model only take around 11 GB to finish that. So that means it's easy to do the federated fine-tuning, the LLM federated fine-tuning with just a single GPU. For example, if you have a 3090 with a 24 VRAM GPU, and also even you can concurrently train more than one client if you have a more powerful GPU. So is a federated trained LLM really useful? Let's just test it with a question. So the question is, what's the ideal day plan in London? And here's the answer generated from a model from the federated training. And you see that the Big Bang and House of the Parliament, London Eye, it seems a very, very nice plan, right? Okay, so how to participate in this leaderboard? It's quite simple. Let's just walk you through the workflow. So as the first step, you just need to choose a task, and then you just design your LLM training based on a given template. And each task will have its own specific evaluation metric. So just test your model with evaluation metric and make sure it has a high performance. And finally, just submit it and secure your spot on the leaderboard. All right. So we believe that your contribution will pave a way to a future where more personalized, domain-specific, and the data-sensitive LLMs will be within the reach of everyone. So that's all the content we will want to share with you about the Flower community initiative. So we finished the summer reproducibility, and we will release the LLM Flower Tune leaderboard soon. Thanks for your attention. We're happy to answer any questions.
Do we have questions for the room? From the room or online? Oh, down here. Let me just take it.
Hello, thank you. Hello, guys. Thank you very much. I think we have been in contact over the Slack community. I just want to ask about the baselines that you are working on. Are they going to be somehow implementable in TensorFlow? Because I have seen some of them more in PyTorch. And I work in both of them, but mainly right now my work is based on TensorFlow, so I have that question.
Yeah, good question. Currently we have baselines on TensorFlow. The majority are in PyTorch because that's what people seem to be preferring, but TensorFlow, PyTorch, XGBoost, we have all three. But you are really free to choose whatever framework you want that is more appropriate for your interest and fits better your hardware, for example. Yeah.
More questions? How about online, Charles? Oh, while Charles looks, I'm going to hand it over to this guy right here.
Yeah, so I'm curious about this LLM Flower Tune leaderboard, how to participate regarding how designed the tasks. So like for the training, evaluation, and the number of the clients, server, it should somehow is already given, or it should be fixed, or because I'm not, yeah.
Yeah, thanks for the question. So, so currently we will release it soon, but we are planning to have a kind of fixed experiment setting for everyone, so that it could just to fair comparison between different methods. Yeah, so that's a current plan.
Okay, Charles, anything there?
We have one person asking if the example for Laura with Flower is already available or not.
The answer is yes. So we already have released the first example, which used Laura to train the model on, as I mentioned, the Alpaca GPT-4 dataset. So you can just try it online.
Perfect. Well, that's it for this talk. Thank you so much, Jan and Javier. I really loved how that talk encapsulates everything that's so good about Flower. We're enabling something that's traditionally known to be difficult, but now it's possible for everyone to sort of start to fine-tune their models, and they can extend it. They can take it to new data sets and so on. Let's transition. We can have our next speaker. His name is Borja Bale. He is a research scientist at Google DeepMind, and he is an expert in many things, actually, but in particular, differential privacy. He's been so kind to come today to speak to us where he thinks differential privacy is heading next, and how we can start to make these methods that are so intrinsically important to federated learning possible and more practical. So thank you so much for joining us today.
Thanks.
Thanks.
For this to show up. Okay. Cool. Hi, everyone. Thanks again for the invitation. It's a pleasure to be here. I'm going to talk today about how we are making progress to make differentially private training practical. And I'm not going to focus so much on federated learning, but obviously the motivation for this question comes because when we're doing federated learning, for example, in a cross-device setting, obviously the motivation is to keep the data on device because we believe that helps with privacy. It aligns with a data minimization principle from the point of view of what we ship to the server. But these systems become very complex, and they come with additional privacy threats that need to be addressed. And one of the important privacy threats that occurs here, but is not unique to federated learning, is the one about what does the deployed model or the final trained model leak about the data that went into it, right? And this threat, I don't know, if you have experience with machine learning, you might have seen, I don't know, you have this kind of sea of weights, there's just numbers, and you might wonder, how could these numbers reveal anything about this training data that went into it? Because I computed gradients, I computed batches, I accumulated for many iterations. Maybe by the end, the model, all the knowledge that went into it from all the individuals and all their examples has kind of been aggregated and is impossible to disaggregate. And the literature is full of examples, literature on privacy attacks, full of examples of actual attacks that show that in many circumstances, like machine learning models can leak information about their training information, right? So for example, we have examples with generative models like the GPT-2 example, or stable diffusion, where with kind of some clever prompting ideas, people have managed to actually like reconstruct some of the training examples that went into these models, like text that appeared only once in the training data of GPT-2, or images that occurred in the training data set of stable diffusion. On top of that, this is not like only an issue for like these super powerful generative models that are driving like this AI wave, but also like occur in much simpler models that we also find quite often in federated learning settings, like classifiers, right? So in classifiers, there's lots of work on membership inference attacks, like the one here from Carlini et al., where basically, like if I have an example, I can detect whether this example was used in training the model with like very high precision. Or if you have like a slightly more like powerful threat model, you can actually show that, and we did this in the paper a couple of years ago, that you can actually extract like individual training examples from just classification models, models that were not designed to generate images. So hopefully that convinces you that the threat of like leaking information when we release the final model is real. And the question is, what are we going to do about it? And if you're here, you might know already the answer. The answer is like we can try to use differential privacy. So differential privacy is not specific to federated learning or central learning. It's just like a mathematical concept that basically says that like if we have a computation that doesn't depend too much on its inputs and has some amount of randomization, will basically make it virtually impossible for an adversary to pull off the kind of attacks that I had in the previous slide. And obviously, like you can write down a formula that expresses that. That's not that important for the purpose of the talk. But we can also put it in a diagram where basically we see, do I have a pointer? Where we see that, for example, like what differential privacy says is that we have a data set with 3 individuals, and one of these individuals leaves the data set, for example, the red one here, and we perform training on these 2 data sets. This is maybe like the real world where my data is in the data set, and this is like an ideal world where I wasn't even in the data set. Then the models that we should be getting out of training with differential privacy will basically be roughly the same, and this is like where this definition becomes precise, which is basically a notion of indistinguishability of these distributions over models. So this has a number of benefits in practice. From this definition, you can see that like it basically implies that you can learn common patterns across individuals without memorizing anything about an individual's data. The framework or the setting behind differential privacy is robust against like known attacks, like the ones in the previous slide, but also future attacks, because there's like a very pessimistic threat model behind the definition, and it's now kind of becoming very established across industry, public agencies, and regulators. But that's not free. It doesn't come for free, obviously. That would be like too good to be true. So basically, it comes with a number of challenges using it in practice, in particular in machine learning context. It can like negatively impact the model utility. It can potentially exacerbate disparities in the fairness across subpopulations, and might be something that like is hard to interpret, like what privacy you're actually getting from this definition. So in this talk, what I'll try to convince you is that like some of these challenges like are addressable, and they're not inherent to differential privacy, but you have to work to get around them. And we're also going to be doing this in like a setting. So the differential privacy has this parameter epsilon that controls the strength of the guarantee. So we're going to be moving in this regime, which is like a smaller epsilon means more privacy. So we're going to be moving between 1 and 8 that like matches like a range of known deployments. Okay, so how do we apply differential privacy when we're training machine learning models? We do that by using like an algorithm that is called DPSGD, which is essentially like SGD. So you sample a mini batch, you compute gradients, you average them, and you update your model with two modifications, as we see here. So the first one is that once we have the gradients from the mini batch, before we aggregate them, we're going to clip them individually. So no individual example has too much influence on the model or the training trajectory, and then we're going to like add a little bit of noise to that aggregated gradient, aggregation of clip gradients, with the noise calibrated to mask the contribution of a single individual, so we get that indistinguishability property that we asked in the previous slide. And we will do this over and over again, like in any iterative training algorithm. And obviously, like you would imagine that this is like a federated learning pipeline where like the gradients come from individual devices instead of being in the server. Now, the important thing here is that like we want like to obtain like a desired privacy loss at the end is epsilon, so something between 1 and 8. But this privacy loss will depend on parameters of our training algorithm. So it will increase with the number of iterations. It will decrease if we add more noise, and will also increase if we increase the batch size. Basically, with this formula here, the formula is not so important. What is important is that this kind of like changes your mindset a little bit about what you can do in a deep learning setting, right? I cannot train for as long as I want until things converge, because like that will blow up my privacy budget, unless when I increase the number of iterations, I'm also increasing the noise, and that will make like my iterations worse, so that might not get me anywhere. So what that means is that in practice, there's a number of challenges in using DPSGD, which is like the bias and variance of the gradients that come from clipping and noise, the limited number of iterations that come from a finite privacy budget, a potential curse of dimensionality because we are adding noise like Gaussian noise in each coordinate, so the kind of the norm, the energy of this noise will grow with the number of parameters. And also that there's like some challenges in working with standard models. If you know, for example, what batch normalization is, batch normalization and DPSGD are not compatible for technical reasons I'm not going to get into. But essentially, what you get is that if you look at like before we started our work at what was the state of the art on two standard benchmarks, CIFAR10 and ImageNet, there was like a massive gap between the accuracy, the state of the art on non-private training and private training. So 71 versus 99 on CIFAR10 and 90 versus like 50 roughly on ImageNet. This is what we try to address in the centralized setting. So first of all, on CIFAR10, what we did is focus on the pre-training regime where the model is initialized randomly, and basically we want to use like this DPSGD algorithm to achieve good results on this benchmark. And the idea was that we wanted to address these challenges that I pointed in the previous slide, and we used ideas from deep learning that existed that basically addressed issues like, for example, like too much randomness or too much stochasticity in the gradients, because that appears in differential privacy, or make training faster, because in differential privacy we know that we cannot make too many iterations and so on. And basically by taking like all these ideas and combining them, these are like, most of them are kind of like standard tricks, except for one that is like, we came up with a new way to do like data augmentation for like that plays really well with differentially private training in the sense that allows you to use several augmentations of the same image in a single update without paying an additional privacy cost. And also, on top of that, like one thing that is like super important, super critical is to do careful hyperparameter tuning. And it's not so much about being careful, but it's also about like forgetting about the rules of thumb that you know. If you've practiced deep learning before, you might have like rules of thumb of how you should set like learning rates or other hyperparameters like that that like generally work. What happens is that like these don't end up working so well when you're doing differentially private training. You need to rethink your rules of thumb. So it's very important to do careful hyperparameter tuning. So by combining all these techniques, what we managed to do is basically to achieve like much better accuracy than previous work. So for example, at epsilon 8, we observed like an improvement of more than 10% over the previous state of the art. And on top of that, we did it with like standard models. So this is like wide ResNets, the bread and butter of image classification in deep learning. No modifications to the learning algorithm, to the model, and what that means, and also because DPSGD like is just like a minor modification on top of SGD. What that means is that like most of these innovations fit really well into existing pipelines, like federated or centralized. But even after putting all this effort into this, like we are still like lagging behind the non-private state of the art on this like relatively simple benchmark that is CIFAR10. And to make this even worse, like to achieve this, we had to throw at this problem like lots of compute. So the question is now like, well, like, is this like an insurmountable gap, or how do we make differential privacy work in practice? And one of the key insights here is that like this is for pre-training. This is with a randomly initialized model. But in many scenarios where we have like private data, we also have access to public data. Might be related to our task, might be like somewhat not related, but we can always use this data to pre-train our model, like the public data, and then apply differentially private training at fine-tuning stage when we're using the private data. So this is what we used in a couple of follow-up works, where we basically said, okay, now we're going to really try to like achieve the smallest gap we can between the non-private performance and the private performance, again on standard benchmarks, but more challenging ones like ImageNet, for example, or Places, and even like chest X-ray classification problems like CheckSpert and Mimic CXR, which are in a medical domain. And what we did there was basically like take this idea that like a lot of people are using now in industry and academia, which is that like we have super powerful foundation models. These are often trained on data that like is free to use, doesn't come from a hospital or like really private siloed data. So we're going to take a model, we're going to pre-train it on that data, make it as good as we can, and then we're going to apply DP at fine-tuning stage. And what happened, what we observed is that like first of all, now the gaps between like the non-private state of the art, for example, on ImageNet, 91, and what we can do with differential privacy at epsilon 8, for example, 88, like these gaps became like very small, like between 2 to 4%. And we observed that like across a number of tasks and data sets. So that was very interesting for us because in the ImageNet case, like the pre-training data that we used is an internal Google data set that's called JFT, but it's kind of similar, right? It's data collected from the web. But on CheckSpert and Mimic CXR, this was also surprising because in here, like the supposedly private, like the private data is like chest X-ray images, so like black and white, where like a lot of detail is important to make sure that you detect like conditions and so on. But the pre-training data here was like data from the internet again, was natural images. So this technique works not only when there's like a small shift between like your pre-training distribution, like the data that you have freely available and the data that is private, but also when there's like a big gap. What changes is what you should be fine-tuning. And that was kind of like one of the super interesting findings in this work, which is that like when you are fine-tuning a model that is pre-initialized, like you might have many options, right? You can maybe like fine-tune the last layer, or you can fine-tune all the layers, or you can fine-tune the first layers, or you can do parameter-efficient fine-tuning if you're using LLMs. So this is where like the crux of the problem becomes very interesting here, because depending on like how different your pre-training data from your private data is, like what you should be doing or what gives you the best results changes. And changes at least in a way that like feels intuitively right, which is that like the closer your pre-training data and your private data are in terms of distribution, the less parts of the model you need to fine-tune, but the bigger this distribution shift is, the more you should actually be fine-tuning. And then as a follow-up of the image classification work, we try to take these ideas, these recipes, and put them in a completely different scenario, which is like synthetic image generation, so training diffusion models, relatively simple ones, like this is not like stable diffusion, these are like for CIFAR10 and Chameleon, which are like relatively small images, but the same ideas like basically work, and all you need to do is figure out like which parts of the model you should be fine-tuning. So if you're interested in this work, I really like suggest that you check out the papers here in the bottom. The other thing we did in this project was basically like look at this point that I mentioned earlier, which is differential privacy. People have seen it in some cases that it might introduce like fairness disparities when you're training, and the idea behind this is kind of intuitive, right? So if differential privacy limits the influence that a single individual can have on the model, it's also reasonable to think that like small groups of individuals also will have like limited influence on the model. And therefore, if my training data set like contains subpopulations, which might be like marginalized groups or underrepresented groups, like people that might feel it unfair if the model performs worse on their subpopulation, then differential privacy might actually like create a trade-off with fairness and exacerbate these disparities. So what we did is like we looked at these models that we trained for Mimic CXR and Checkspert, so text ray classification problems where like on top of like the conditions associated with each image, we also have demographic attributes like age, race, and sex, for example. And basically we did an analysis following like recipes that other people have produced for analyzing the fairness of these chest X-ray classification models in the non-private setting. And what we found was quite surprising, which was that now that we have these like very accurate private models for training on these problems, the disparities that the private models exhibit are actually comparable to the disparities that the non-private models exhibit. That is not to say that the private models don't have disparities. It's just to say that like the disparities are the same regardless of whether you're training privately or non-privately. And we believe that the reason for this is because like the previous studies that had looked at like the disparities in private models were using kind of outdated recipes in the sense that they were obtaining models that were not very accurate. And here in our study, like the models that we're comparing, there's like a very little gap in accuracy between the private and the non-private models. So for example, to illustrate that, like you can take like the disparities across like several like demographic subgroups in your test data set and compare the disparity between like a private model at epsilon 8 and the disparity at like non-private model, so epsilon infinity. And here the disparity is basically defined between the AUC on the subgroup minus the AUC on the overall population. And what we see is that like for most of the subgroups, like these two disparities are concentrated around the diagonal, which basically says that like both models are exhibiting the same disparities. But obviously, like here we have groups of different sizes, right? And the intuition suggests that like if some groups are going to be worse on the fairness side, are going to be the smaller groups. So then what we did is like look at like say the y-axis minus the x-axis here, so like how far we are from the diagonal, and plot it against the size of the group and try to see if there was like a systematic effect of the group size on the difference on disparities. And basically we observed like a negligible effect. So our conclusion is that like at least in these cases we analyzed, like this is not like a general statement because it cannot be, like there's theoretical results that say that if I look at very small populations, like I'm going to observe this. But in practice, in these data sets that we have looked, which are representative of stuff that like people use in practice, if we believe like people who use that to develop like medical and healthcare related models, like differential privacy doesn't necessarily like introduce worse disparities. Okay, so I have roughly 1 minute left, so I just want to flag that like all the research that I've showcased here like is built on top of a single library that it's open source. It's called JAX Privacy. It implements differentially private training end-to-end. If for the server side, if you want to play with it, it comes with like some reusable components which can also be used in other pipelines. It works out of the box on GPU and TPU. It can accommodate any type of JAX-based models. I know JAX is not very popular outside Google, but it's really cool, so try it out. And by default comes with like support for large batch sizes, which is one of the things that you need to achieve good accuracy. And on top of that, we've made like an extra effort to make sure that the library is correct, because like implementing differential privacy is not always trivial. Okay, so conclusion. I hope I've convinced you that differentially private training for machine learning models is coming of age in the sense that we have techniques that work with standard models and just make minor modifications to standard optimizers or training pipelines. They feed the techniques that work well feed really well the paradigm of like a pre-trained foundation model on non-sensitive data plus fine-tuned on the private data. And you can achieve competitive utilities without negative fairness side effects. If obviously a lot of the people here care about federated learning, but I still believe that server-based training is a good playground for making progress on the privacy utility trade-offs of DP training. And obviously, like we are going to hear, and we've heard in the previous sessions about like many other issues that arise in federated learning when you want to use these things. But I don't know, we have way better experts about this in the room, and I'm also happy to chat offline about like some of my thoughts here. I'll take some questions now if there's time. Thank you.
We have time for questions. That was a great talk. There's a question right down here.
Yeah, thanks for the nice talk. So first question is about the batch norm. So you mentioned that you basically can't use the batch norm in DPSGD. So can you provide some intuition on why this happens? Yeah.
Yes, so basically batch normalization like crosses information between examples in a way that is not through kind of the gradient updates. So what that means is that like you can potentially try to like apply a privatization mechanism in the update of the batch norm statistics at every iteration or wherever the statistics are updated. But this will not kind of come for free in DPSGD. Like you would need to apply like specific mechanisms separate from DPSGD to privatize like the batch norm statistics. And it would introduce like further kind of degradation of utility potentially because that mechanism would have noise. So the work that I've shown, like I didn't get into the specifics, but basically like in the wide ResNet applications, like we use group norm and it works similarly well as long as you do proper initialization. And in the larger experiments in fine-tuning, like basically we use like work that developed by some of the co-authors that is called like normalizer-free networks. So these are networks that are designed by scratch with very minor modifications to ResNet type architectures to not need any of these normalizations to train fast.
Yeah. Second question is a kind of broad question because you mentioned the privacy issue in large language models. So I want to know your thought on how to make LLMs more private, because I know if you just use the DPSGD, then the training just fails, right? Yeah, thanks.
Yeah, that's a good question. I think like here I probably can refer you to works that have been coming out of Microsoft research in the last couple of years. So they've done a lot of work on private fine-tuning for LLMs. Pre-training, out of the question, I believe. But fine-tuning, especially if you're using parameter-efficient techniques like LoRa or others, it's still manageable because that parameter-efficient fine-tuning, what it does is it reduces the dimensionality of what you're training so much that then you don't suffer from this course of dimensionality and you can achieve good results. So I do think it's possible in some settings.
Thanks.
Cool. Got a question there from Andrew. Ruth.
Thank you for a great talk. I'm just curious on your thoughts on how, in the context of, say, a continual learning algorithm, or say, let's say one implemented a system in medical practice that was continually updating, would there be, say, a minimum update size in terms of training examples for you to be able to maintain differential privacy, or is that something that would technically be difficult, or what are your thoughts on that?
Sorry, just a minor clarification. Are you thinking of like is this like continual learning something like federated learning, or is it more like, I don't know, every year we update the model?
Let's say in the context of federated learning.
Okay.
So you'd say you'd have a model that you've trained once, you've implemented it, and you're looking at doing an update in performance by scraping the last, say, month of patients' data. Is there, say, to keep it private, would you need to have a minimum size? And if so, how does one determine that? Or are there other ways around that?
Yeah, there is no minimum size in principle, but the more people that come, like the more individuals that are included in the update, right? The larger your batch size, doesn't matter if it's centralized, continuous, or federated. Like the larger your batch size, the better your signal to noise ratio is going to be in your individual updates. So the more utility you're going to get. Like differential privacy will just like add some noise, and that noise like will have more or less influence depending on how many individuals are part of that like update. Now, the one thing that is worth keeping in mind in this kind of continual setup, like I don't know like what the range of continuity is here, but like if we're thinking like years or decades, potentially like the privacy loss of the individuals will accumulate over time. So your kind of privacy loss would keep growing, right? In the same way that it keeps growing as I do more iterations in the DPSGD. But like, it's a very interesting question to think like what that means in this setting, because also like the patients will keep changing themselves. So maybe like what their medical records look like 5 or 10 years ago is not so private anymore from their point of view versus like what their medical records look now. So that I think is a problem that hasn't been looked at too much, and it's really interesting to think about.
Thank you. I guess to use an extreme example, let's say you had an update of one individual, presumably that wouldn't be possible, or you'd have to add noise that counteracted the contribution of that individual to keep them differentially private, or was that?
Yes, exactly. So like the noise would be the same, right? Because the noise is the same, but then like when I average, like if I average between like 10,000 individuals, like that noise gets reduced. If I only have one individual, like I'm not averaging, so like that noise stays there, and actually like it's possible that like it actually harms your model more than just learning. That makes sense? No, thanks.
Great. Oh, I think we're running out of time for questions. So thank you so much for the talk. It was perfect. Thank you.
Thank you.
Yeah, I really like that practical kind of view on how DP can be useful. So our next talk is going to be by Professor Kang Yong Lee. He is leading one of the top federated learning labs in Korea. And so he really is pushing a lot of the work in federated learning in Korea forward and deploying it in many different scenarios, including medical-related ones. We've been working with this lab now for more than a year as a design partner. And he's going to tell us about recent work they've done that builds on Flower, but provides a new functionality that's been very useful for many different types of settings. So thank you so much for joining us today. Thank you.
Wow. Thanks for the introduction to me. And it's very glad to speak about my progress. FedOps is my brand name. And it's enhancing federated learning framework with Flower for the federated learning marketplace. So I had a chance to explain about FedOps, what it is, to kind of tool to simplify, pick up AI model, and then make a life cycle management for the federated environment. So we have 5 functions, basically, FL scalize, and the manager functions each side, and also the contribution evaluation and client selection, and also the integrating blockchain federated learnings, and also distribution models, and then also provide monitoring functions, all of these. So it is basic FedOps functions, and we provide as a community base. So it's almost same as Flowers, and top up Flower and install FedOps, then we can automatically install Flowers, and we can enjoy the federated learning environment. Also support GitHub and the Slack. So the people engaged in these communities, and we provide the solutions to them. So today I'd like to explain more about functions and the use cases we are considering this time. So baselines and already explained, and we support monitoring, simulation, and to monitor 1D, we integrated the base function and the silos. We brought the specific use case for by using RMECS. It's the local model emulation for client selection. Basically, the client selection is one of important issues. So based on gradient or loss or AUC and accuracies and many ideas how we select the client for the heterogeneous management. So we provide what is the best way to select the model. And also we are explaining this downstairs as a poster, so you can see it. And also, we are implementing dynamic adaptive optimization, which is, there are many cases to select a client. So what is the best way to select the client? So dynamically adaptive select the client, we will provide it. And the mobile case, so we support Pluto Manager. So one application can support iOS and Android together. That's quite a unique function by FedOps, so we can enjoy. And also it was tested by AWS Device Palm as well. And also provide certain several use cases as an industry pack. So the SAMD is on downstairs posters also explain about this. It's cases, so we'll explain more about this. SAMD, we call this software as medical devices. So hospitals has kind of, the scenario is a severity classification, the emergency room, emergency department, how we manage once the patient come to the emergency room, then we can arrange the severity and then to manage the patient. So there are big data set in managed by Korean government. It's 11 million record, more for emergency medical records. So, and also gathered from 72 hospitals. So it's big data, and we allocate newly and then cross silos and make solutions and applying RMEC as our client selection solutions and make a result. So you can see the posters and then that's the result. And it's the cross-device mobile solutions, so the Plutos so we support, so we can support iOS and Android devices as well. And also it support tested on AWS test cases. And another scenarios we are shooting for the cases is one is decentralized clinical trial. From the centralized to decentralized is current trend to how we apply. So this clinical trial is this time everybody need to be in the hospital or CTC, so they need to give the data and so on. But it's need to make a data at home or their places and aggregate, and then we can provide. The solution is the DCT. So there are two ways. One is cross silo. Is the many hospitals come together for the specific disease, then they can use cross silos. And also they can use device, cross-device solutions at home as Federated Learning client, and also the hospital side as Federated Learning servers, and we can make together. So, and we need to consider more about the my data. In Korea, we call my data. England, my data, and Sweden is my health. It's kind of personal data treatment management. In Korea's government manages a certain site and put the my data and get the data, and we can and treat. So personally, he can manage and he can get incentive from my data, so and so on. So it is new requirement how we integrate together this solution. So we need to consider more on these areas. We are considering to deploying these scenarios. And it is also pharmacovigilance is scenario. So prevent adverse effect or identify hazard and minimize risks. So get information from hospital, institution, and personnel, and publications, and then we identify what are hazards, so how we can minimize the risks. So we need to consider more about it. Also, we can think about his individual my data, and then how we apply to the solution. And also, hospitals many hospitals has their own common data models. So we get the data models and keep preserving the privacy, and then how we aggregate and then generate the information. That's another consideration to support CDM and as a CDM PALM, and then make a Federated Learning application is the new consideration. So it is kind of multi-centers, multi-institutions, or the multi-organization is they need to collaboration, and also they need to compete together. So to provide this kind of multi-organization solution, we need to require, and it makes a certain kind of marketplace and industry requirement. So Melody is one of famous the Federated Learning use cases for the Parma new direct discoveries by using ledger solutions. So we need to consider with how we manage the individual contributions for the institutions. So blockchain kind of smart contract or ledger solution integrations and evaluations and securities, those are our research items to consider more about. So it is kind of general framework to provide co-opetition framework. So now we are approaching to the market. It's like FedOps is still considering about how we aggregate personalization and the client selection strategies. These are focused items we need to research continuously, and also combining blockchain, BCFL, and securities. That's the basic research areas. And then top of Flower. Flower has the baselines and so and other experience to provide the solution to commercially, and then we combine our FedOps the service model and into the market. It's getting the larger and larger for Federated Learning requirement. It makes Fed marketplaces. So generally industry the market, and also pharma and medical, finance, energies. We already saw several talk about the energies. So it is, we are going to the marketplaces. So we are preparing and then make on the cases with the Flower. That's what I am doing. It's, thank you for the listening. Thank you.
So we have time for questions. Do we have questions in the room or online? Let's start with online, since we've been neglecting them a little bit. Charles, anything there? Not yet? Okay. How about in the room? Any questions? No, I guess, well, while we wait, I mean, one question I had was, how much faster do you think using the FedOps platform does it make somebody if they want to build an application or system?
Okay. Yes, very good question. So we can, if you bring certain the models, machine learning or AI models, then quickly we scalealize and then learn, and then So, and then you can see. So Kubernetes environment that makes time to learn, but 1 hour, 2 hours, you can, if the application is simple, then you can deploy very easily.
Okay, great, great. So much, much faster. Any other, there's a question down here.
Yeah, well, hello, thank you very much for the presentation. One simple question, I saw that you were working mainly on cross silos, right? But is this solution also applicable or usable for cross-device federated learning?
Oh, actually, we cross-silo models that we are implementing for the emergency room severity classifications, and also cross-device for the many devices, iOS and Android is. So we have different use cases as well. So tomorrow we will have new posters for cross devices.
Great, so see you tomorrow. Thank you.
Thank you.
Well, let's thank the speaker again. Thank you so much.
Thank you.
So we're going to make a slight departure from the actual program listed to transition to our next speaker, which is going to be Virginia Smith. Virginia Smith has joined us online. She tried very hard to be here in person to give her viewpoint on privacy and federated learning. She really has been one of the leaders since the beginning. She is the Leonardo Assistant Professor of Machine Learning in Carnegie Mellon. Her research spans machine learning, optimization, distributed systems, and she's obviously won a number of awards for the many seminal pieces of work that she's done. Most recently, I noticed that she won the Samsung AI Researcher of the Year Award, if I'm not mistaken. So that's a wonderful credit to both her and her students, I'm sure. Virginia, can you hear us fine?
Yes, yeah, can you hear me? Okay.
Great, great. I'm sorry that we don't have a camera so you can see everyone here and online. Yeah, over to you. Thank you so much for being here to join us.
Perfect. Thank you so much for having me. And yes, I really wish I could have made it there in person, but I really appreciate the opportunity to still speak with you all virtually. So yeah, as was mentioned, a lot of my research, especially over the last several years, has been in the space of federated learning. And today I'd like to talk about two critical concerns in the federated learning space, one being privacy and the other being accuracy, and accuracy specifically through the form of personalization, which is really crucial when you're thinking about accuracy in heterogeneous networks like practical federated learning systems. So before I get to that, I know everyone is quite familiar with the space of federated learning, but I wanted to start this talk off with a very brief motivation. And I want to do this partially because I have, a lot of people come to me and say, where is federated learning going? Is this still an important problem? Do people still care about the, applications of federated learning? And I think there's an obvious answer here for why federated learning is important and will continue to be increasingly important moving forward. And that's very simply, if you think about existing and future applications of machine learning, you might be thinking about things like language models or machine learning for healthcare or smart homes or smart cities. These applications all rely on data, and they rely on lots of good data, right? This is something that we've seen over and over again, that data is a really critical differentiating factor in these applications. And more frequently, to get access to all of this data, we have to go beyond the data of a single user or a single hospital or a single sensor, right? We have to gather data from multiple sources and across multiple organizations and from entire networks of sensors, right? And this is where federated learning can be incredibly useful. It can help you to process and gather and obtain knowledge from this data more efficiently, more effectively, and in a way that improves privacy and security. So in thinking about some of these, key concerns in federated settings, at its heart, you're trying to solve some distributed learning problem, right? You have a network of clients, distributed clients, and you're trying to train some model over these clients. But there are a number of things that make this really unique and present new challenges beyond existing work in distributed learning. So if you think about cross-device FL, like was just mentioned, there can be major concerns here around efficiency, especially the cost of communication. You might be learning over massive, slow, or unreliable networks. Privacy is a major concern. This is one of the motivations to perform federated learning in the first place, but we're still sending information over the network. There are still ways that sensitive information might be leaked. So it's really critical to think about how you can still ensure privacy throughout this process. And then finally, another key way that federated learning differs from something like standard distributed learning, say in a data center setting, is that because the data is being generated and gathered on these edge clients, the data might be very different from one client to another, right? You might have unbalanced or non-identically distributed. You might have heterogeneous data. And this heterogeneity can show up not just in terms of the data, but also in terms of the underlying devices or clients and their computational capabilities as well. So this, these broad challenges, these are things that I have been spending a lot of time thinking about over the last several years. My group and I at Carnegie Mellon have been developing foundational tools for the field of federated learning. We've been, developing techniques for efficient distributed learning, focusing a lot on this issue of heterogeneity of data and systems, and also more broadly developing solutions for trustworthy machine learning, including things like privacy and robustness and fairness, and thinking specifically about their application to federated learning. A major part of this has been partnering with folks who are deploying federated learning in practice. So we've developed solutions that have been deployed at places like Google and Apple and Meta. We've worked with partners at Symantec. We recently proposed a solution that was a winning solution to this Privacy Enhancing Technologies Prize Challenge, which was looking at privacy-preserving cross-silo pandemic forecasting. So I'll talk a little bit more about that later in the talk. And we have really, been from the get-go quite interested in developing tools that are reproducible and open source. So, I think Flower is a big part of this, and we've also developed some of our own, tools here, things like the LEAF benchmark for federated learning. And I have also been helping to run this Flow seminar, which is a weekly worldwide seminar which covers topics in the space of federated learning. So this is open to the public. It takes place over Zoom once a week. And if you're interested in this space, I would definitely encourage you to check out that seminar. All right, so that was a brief overview and motivation. Today, I want to talk to you about two concerns specifically. I want to talk about this issue of privacy and this issue of heterogeneity. So I wanted to talk about, how we can reason about these concerns and also how we might be able to tackle them, and specifically what sort of tensions arise between these two challenges of privacy and heterogeneity. I'm going to talk about this in two contexts. I'm going to focus first on thinking about privacy and heterogeneity in cross-device federated learning. And then I'm going to talk about some solutions in cross-silo federated learning and how they differ a little bit from what we developed in the cross-device space. And in the second one, I'll touch on some of the techniques here that we used as part of a winning solution to this cross-silo pandemic forecasting challenge. All right, so starting off thinking about heterogeneity broadly, this really boils down to, I think, there's a lot of ways you can think about the issue of heterogeneity, but one of the key concerns that this brings up is if you know that the data differs from one client to another in a federated network, how should you incorporate this information in terms of your model? How should you be modeling federated data? And there's a couple natural extremes to consider. You could learn completely local models, one model for every client in the network. This is, super personalized, but you're not learning information from clients that might be related to one another, right? This is the whole promise of federated learning, that people might have data that might be useful for, other clients in the network. And so the other extreme, is to learn just a single model across all of the clients in the network. And the clear downside here is that there might be, a limited capacity to then learn the unique personalized behavior on each of the clients. So ideally, we might want something in between these two extremes. If we know that data might differ in various ways from one client to another, which is very common in federated settings, we might want to be able to learn between relevant related clients in the network while still sharing information, but developing models that are personalized to the unique behavior on those. And this is something that we propose right sort of from the get-go in terms of thinking about the problem of federated learning. This is one of the key insights we had many years ago now at this point, which is this can be naturally addressed by developing solutions for personalized federated learning. And specifically, a key tool here, which has become very common, is to think about using techniques for federated multitask learning. So in multitask learning, the idea very simply is that you can learn separate models, one for every client in the network, but that you can also learn about the relationships that exist between those models or those clients. So this is a super broad framework. I'm just, providing a very broad instantiation of the objective here. But you can think about, incorporating different, penalties in terms of this regularizer, for example, to learn information about, the weights on the edges in a graph where you assume that all of the clients are related. You could learn that there are outliers that exist, that clusters or groups form amongst the network, or maybe that there's some asymmetric relationship. And crucially, what's nice about this is you don't need to know these relationships beforehand. This is something that you can learn directly from the data. So this makes this a very powerful tool for learning over heterogeneous networks. And we've seen this over the last several years. We've looked, specifically at trying to rigorously study the benefits of multitask learning and personalization in federated settings. So this is something that can improve accuracy, but it also has other advantages. It can improve robustness to attack. It can improve fairness of the model across the network, so ensuring a more equitable performance of the model across diverse or heterogeneous networks. And we were quite curious about what the potential advantages or possibly disadvantages of something like multitask learning might be in relation to privacy. And here, I just want to note something broadly, which is that privacy is not a binary metric. It can mean many things. And in the context of federated learning, it's important to think about, where sensitive information might be leaked, right? If you're thinking about learning across a set of clients and developing a model in a federated setting and then deploying that, you might see a workflow that looks sort of like this. There are multiple places where sensitive information could potentially be leaked. You could gain access to the specific clients. You could learn about information being sent over the network. You could gain access to the server, or perhaps, some of the models or metrics that are being developed by an engineer. And another one, which is, I think probably the most common one, is that you can learn information from the model that's actually being deployed, the final model that's learned. And there are various strategies that you can think about for enhancing the privacy and security across various components of this workflow. I've seen that there's going to be some talks, talking about various aspects of this in the context of federated learning. For the talk today, I'm going to focus on this issue of how can we ensure privacy in terms of the final model that we're learning. And this one I think is quite important because this is definitely something that we're going to be giving people access to, right? The whole point is to learn a model that we can then give access to the clients so they can use that model, right? So this is something that we're going to basically be giving to everyone, and we definitely want to make sure that this doesn't reveal any sensitive information. Okay, so how can we ensure the privacy with respect to this final model that we're developing and deploying in federated settings? A very popular and common technique here is to use differential privacy. I'm not going to go into too many details of this, and I assume that many of you might be familiar with differential privacy, but at a high level, the goal is basically to learn as much as possible about a group, to learn this broad aggregate model while learning as little as possible about any individual in it. So you're trying to learn a model without learning unique, distinguishing factors about the clients that were used to train that model. Okay. In the context of something like multitask learning, this can actually become sort of challenging, instantiating this notion of differential privacy. And the reason is that if you think about, cross-device federated network, typically what you're trying to do, the metric or granularity of privacy that you care about, is with respect to the individual clients, right? Each of these devices typically represents a client in the network, and we might want to learn a model that, takes in to account aggregate information from all of these clients, but doesn't allow us to say, definitively that a particular client and that client's data was used for training. The reason this becomes difficult with respect to multitask learning is that we're also trying to learn models that are personalized to the unique behavior of each of the clients. And what you see with something like traditional differential privacy is that if you naively apply it in conjunction with multitask learning, you get really, really poor performance because you're learning models that are, unique to each of the individual clients while also trying to ensure that you don't know that that client's data was used to train that personalized model. Okay, so this is a natural tension and an issue with just using traditional DP in the context of something like multitask learning. Okay, what else can we do? What we did in this work is to think about a different, I think very natural relaxation of differential privacy, which is commonly referred to as joint differential privacy. The key idea, which I think is very simple and straightforward, I'm not going to go into the algorithmic definition. Basically, the idea is that we want to ensure that no sensitive information from other clients beyond a specific client is used to train the personalized model for that client. So we still allow there to be a dependency for, say, user one when developing user one's personalized model on user one's data, but then we have differential privacy in terms of the other clients in the network. So there's this natural sort of decoupling where you can, maintain the, I think, important accuracy that you want to maintain by learning a model that's personalized to each of the users, but you're ensuring that that personalized model doesn't leak information about the other users in the network. Okay, so I'm not going to go into the specific details of kind of the theory and the algorithmic details here, but I just want to point out some of the key results from doing this. So by using this variation of differential privacy, using this joint differential privacy approach, we were able to get good performance with using multitask learning in a cross-device federated network. And until this point, it was sort of unclear how to actually use multitask learning, which gets this, these great accuracy, robustness, fairness, benefits in practice with differential privacy, which is sort of the gold standard of privacy in federated settings. And we were able to do this with joint differential privacy. And there's two key results here. One is that by doing this, by using this, privacy formulation, we see that our private versions of multitask learning retain sort of the same benefits that you would see in non-private settings, now in private settings. So what I'm showing in this plot is that you see that when multitask learning is useful in a non-private setting, when we then look at instantiating this private version of multitask learning, we get some of the same benefits that we saw in a non-private setting, now in a private setting. What was interesting, though, is that we also saw that it could have additional benefits. So even in scenarios where multitask learning in a non-private setting didn't seem to be super, super helpful, so maybe we weren't in a super heterogeneous environment, we saw that when we moved to a private scenario, so we were training with differential privacy, actually now there were pretty major advantages to using private multitask learning relative to just learning a single model in a private way. So this was really exciting to us, and it encouraged us to dig a little bit deeper and think more about this problem and why we might be seeing these advantages in terms of using private multitask learning and what other applications there may be. And specifically, we looked at how we could apply private multitask learning in cross-silo federated networks as well as in cross-device networks. And an important distinction here arises in cross-silo federated learning in terms of how you think about defining privacy and the granularity of privacy in a cross-silo network. So in particular, in cross-silo settings, you usually don't care about the privacy of the entire client or data silo as much as you do about the individual components of that silo, right? So in a cross-device network, you often think about these clients as being users, and you often care about user-level privacy, right? You want to ensure the privacy of each of the users in that very possibly large-scale network. In a cross-silo setting, typically, say you're learning over 10 hospitals, typically you know that those hospitals are participating in this procedure, but what you care about is the privacy of the individual patients in those hospitals. So here you typically care less about this notion of client-level DP and more about a notion which you can refer to as silo-specific item-level differential privacy. So you care about the privacy of the individual users within each of these silos. So this is important in the context of multitask learning because it changes a little bit how we think about some of these baselines of just learning a local model or just learning a global model. And what you see here actually is that just doing local learning, which in cross-device federated learning is essentially free from a privacy perspective. You're not paying, you're not eating into your privacy budget from doing local training. Here in a cross-silo network, you do start to pay a cost when you do local training. Okay. The ramification of this is basically that what we saw is that in terms of thinking about private multitask learning with this specific notion of silo-specific item-level DP, there were simpler sort of multitask learning baselines that seemed to do really well relative to things that from the cross-device setting we think of as being pretty competitive, things like learning a global model and doing fine-tuning. In the cross-silo setting, this simple fine-tuning baseline, actually you start to pay a big cost for doing this when you're trying to implement this with differential privacy. And what we saw instead is that this simple multitask learning objective, mean regularized multitask learning, this very simply says learn separate models for each silo in your cross-silo network, but make sure they don't deviate too much from the average model. This seems to work actually quite well. This is something that we explored both in theory and in practice, and it has particularly nice sort of privacy utility trade-offs. So this is something, as I mentioned, that we studied. We have a few papers on this topic, but we also went and actually implemented this. And we implemented this. We were excited to see recently this, US-UK Privacy Enhancing Technologies Prize Challenge. So this was a broad set of challenges, with roughly $1 million in prize money. And we specifically were looking at trying to, see how useful some of these tools that we had been developing would be for the problem of privacy preserving cross-silo pandemic forecasting. Okay, so the goal here specifically is that you might want to be able to, I think for obvious reasons that we're unfortunately all quite familiar with, be able to predict whether or not, a pandemic or a disease might be spreading across a population. And you might want to be able to do so given access to siloed information, maybe from different hospitals, for example, or different health districts. But crucially, you care a lot about the privacy of the individuals that are sharing this information, right? So you want to be able to do this in a way that maintains that silo-specific item-level differential privacy. Okay, in thinking about a solution for this, we did the following things. So we formulated this as a federated binary classification problem, trying to see how likely a certain individual was to be infected. So what is the likelihood of spread of this disease? Then we used specifically this silo-specific item-level differentially private training. We looked at using model personalization via multitask learning, and we specifically used this approach that we had studied theoretically and shown that it had some key advantages. We used this mean regularized multitask learning approach. And these were sort of the key components. This was a major component in developing this winning solution to the privacy preserving pandemic forecasting. Okay, so let me stop there. I think I'm almost out of time. But the key takeaways from this, the key sort of, punchlines from this work, one is that in the context of federated learning, you have some clear privacy advantages, right? In the sense that you're not sending and sharing all of that data into one central location, but it's still important to think about where sensitive information may be leaked throughout this process. And specifically when you're thinking about differential privacy, which is quite important in the sense that, you want to develop a model that is eventually going to be deployed across these different clients. It's appropriate to, you need to think about how to appropriately define various granularities of differential privacy for the application at hand. So we talked about two specific notions. We talked about differential privacy in cross-device settings through this joint differential privacy approach, and we talked about this silo-specific item-level DP for cross-silo federated learning. Another key takeaway is that multitask learning provides quite significant benefits in private settings. It provides benefits in the sense that if you see that multitask learning is useful in non-private settings, which we've shown that this is useful not just for improving accuracy, but it has these other advantages as well, that you retain those benefits by thinking about these private multitask learning approaches. But that there are perhaps even some advantages even when you don't see initial success from multitask learning in a non-private setting. So this is something that I think is quite interesting to continue exploring in future work. And finally, one of the other takeaways from our work, especially looking at this challenge, is that actually quite simple, highly scalable methods for multitask learning can work quite well in practice. So these are tools that I think are not too difficult to modify existing solutions from, and are pretty easy to get implemented and running in realistic federated applications. In terms of future work, we're continuing to explore additional forms of multitask learning, better understand some of these privacy advantages that we've seen a lot in practice, and develop further general understanding of heterogeneity. We talk a lot about heterogeneity, but I still think we need better examples of exactly what this looks like in practical federated applications. As one effort towards this, we developed this Motley benchmark recently, which is trying to get a closer look at federated learning and realistic federated applications. But I think this continues to be an important ongoing area of work. Great. Thanks. That's all I had. I don't know if I have any time for questions.
So we have time for questions. So any questions from the room? At all? Or online, perhaps? Oh, okay. There's one question on the back there.
Thank you, Virginia, for interesting talk. Actually, I have a question. Are you going to target any kind of standards on the data side in the future?
Oh, so I think the question, sorry, I faded out a little bit at the end there, but the question was, are you going to target what solutions on the data side? Is that right?
Standards regarding data.
Oh, standards regarding data. So by that you mean
for example, in healthcare, we have different standards for managing the data and using the data in the federated settings. For example, OMOP is one of the popular one. So these kind of standards, because they can bring high quality data for federated learning environments.
Yeah, this is a good question. I think that this is something that is really important for the field. In terms of I mentioned this on the previous slide. I think we need better examples of what something like heterogeneity looks like in practice. I think we also need better examples of what these sort of standardizations might look like in practice for different federated data sets. This is something I've been thinking a lot about personally in the context of privacy. So I've been thinking a lot recently about the problem of unlearning, that you might learn a model and then, for various privacy reasons, in terms of the data sets, people might want to delete their data or make modifications to the data on each of the silos. And so you need to think about updating the model that you've learned. I think this is another area where we need a better sense of how people can formally make these requests and what that looks like in practice, and what sort of guarantees we can provide about the final model. But I think going back to the question, one thing I'm quite interested in here in the context of data standards is also thinking about when there might be heterogeneity in terms of the data formatting and standards in a federated network. So this is something that we've been thinking a little bit about. And I think that form of heterogeneity is not often talked about, but might be a real issue in practice.
Great. We have one more question at the front here. Yeah, I'll just hand over the mic.
Hi, Virginia. Thank you for the talk. It's great things you're doing there. Today, there's been a lot of discussion about the applications of federated learning, and which all seems to be predicated around deploying within organizations that own data. So I wonder, in your research, have you looked at communities rather than organizations? So we know we can talk about communities of practice, communities of interest, communities based on localities. You know, these have their own data, their own outlook, their own concerns about how they want that data to be stewarded, and they want to retain ownership rather than being maybe what we could call strip mined. So yeah, this one's.
Yeah, I think this is a really important point. One way that we have been thinking about this recently in terms of our research is in developing tools that incentivize people to share data. This is not something that's often talked about, especially in maybe cross-device applications of federated learning, where you know, even though you're trying to improve privacy, you assume that the company owns that data and has access to all of the data. And so you don't necessarily need to incentivize clients to share their data. You assume that you have access to it, right? But in other applications, like applications you're mentioning, we want not only privacy and security guarantees, we want an understanding of, you know, how our data is going to be used and what we're going to get back from that data being used, right? And I think this is a scenario we've looked at, even very simple definitions, like if you share your data, you want to make sure that the model that is learned is at least better than if you had ignored everyone else's data and just learned a model on your own local data, right? This should be the bare minimum that we provide in a federated setting, right? You're at least getting something back for, you know, this effort of sharing data. And there's many more complicated instantiations that you can imagine. So this is something that I think is really important for the field moving forward, is to think about these incentive mechanisms. And this is something that we have been exploring in our recent work as well.
Great, amazing. So then with that, we're going to go to break. Thank you so much, Virginia, for the talk and the wonderful dialogue afterwards. Thank you so much. So that's the end of session 2. We're going to take a 20-minute break. Please stretch your legs, have something to eat, and we'll see you back at 4:50. Thank you. Okay, everyone. We are going to start with the last session of the day. So please take your seats. Yeah, the last session is about to start. It's a pretty amazing session. Okay, we're starting soon. Please take your seats. Okay, please take your seats. Let's start. Thank you, thank you, thank you. Okay, well, to start session 1, we're going to have a talk being given by Minha Almam. So Minhal is an assistant professor at UNC Charlotte. He also has an affiliation with Stanford. And he's going to be telling us about a piece of work he did in collaboration with a number of institutions that relates to how you can examine the construction, the training of models that examine different types of eye conditions. But he took the path of training this in a federated manner. And so with that, I'm happy to hand over to him if he's online. Great, he is. Thank you, Minha, for joining us today. I apologize that we don't have a camera for you to see everyone here, but it's basically a room with a number of people who are just super excited to hear from you. So I'll hand over to you now.
That's great. Thank you for the intro. Great to be here. I wish I was there in person, but Zoom it is. My name is Minhaj. I'm currently the director of the Quantitative Imaging and AI Lab at UNC Charlotte. I do have some collaboration and affiliation with multiple institutes here, Stanford and Illinois more specifically. So today I'm going to talk a little bit about federated learning and its use of diagnosis in macular degeneration or overall in retinal diseases. Most of the retinopathies are ocular manifestation of systematic diseases. For example, diabetic retinopathy is ocular manifestation of diabetes, and nearly 40 to 45% patients with diabetes are prone to vision impairment from DR. And it's projected by WHO that by the year 2040, it's going to be more than 200 million people who will be somewhat affected by this kind of vision impairments. In this kind of retinal diseases, what happens is that there's retinal pathologies like aneurysm, exudates, and hemorrhages that affects your retinal tissues, and there's a reduction of oxygen. Because of that reduction, there's a protein called VEGF, or vascular endothelial growth factor, that signals our brain that we need more oxygen. And the only way the brain can react to that is create more blood vessels, so that blood vessels can take oxygen to those retinal tissues. However, because this growth of these abnormal blood vessels are abnormal, they leak and there's hemorrhages, and that can lead to vision impairments. So that's one of the main ways of getting affected by systematic diseases. AMD, the disease that I'm gonna be most talking about is also a retinal disease, mostly affect the macula, which is, I don't know if you can see my mouse is around here. We're looking at the retina here. It has become a global pandemic. The rise of AMD disease in population correlates with the increase of mean age of human, because there is a much more older population globally because of the mean age has increased. And that's why AMD is prevalent in American and European countries, and nowadays it's showing its prevalence in Asian countries as well. AMD causes manifestation of this kind of pathologies like drusen and liquid formation, and that affects the macula, which is the center of our eye. And this is what a person with impairment with AMD, their vision looks like. So we can see that there is a prevalence of retinal disorders, and millions of people have already been affected by, is being affected by these retinal diseases. And this includes adults and children. So there's a need for automated diagnosis and assistive technology for managing these diseases. And imaging actually plays an integral part in diagnosing these retinal diseases. A sample here, this is called optical coherence tomography, OCT, and optical coherence tomography angiography, which shows structural and vascular information and flow information in the retina. So this is captured in devices in our lab, where we can see the vasculature and retinal structures in the cross section, and also a 2D projection. So overall, these OCT modalities provide structural, functional, cross-sectional information on retina. And we can see here like high resolution vasculature. If there's a vessel dropout, then we can see the onset of the diseases in these imaging modalities. So, and also these, there has been quantitative features, imaging biomarkers that have been developed, especially by our lab, which can correlate to microvasculature and foveal changes in the retina. And these features give a measure of geometric and textural complexity, and are very good in identifying different stages of the disease. However, although these features are really, really useful in identifying stages and pathologies, there's a need for artificial intelligence-backed models that can do some work for us. So in the field of ophthalmology, AI has seen huge success, especially in triage. So the idea is we use AI to triage people. For example, if you go to a point of care doctor, your retinal image is taken, and then it's companies like Digital Diagnostics, INUC, Retina AI, which have been FDA approved, they mostly work on triaging. So it will flag you that you should go see an ophthalmologist or not. And then the idea is that you use those features and like other advanced imaging techniques to actually diagnose, manage your treatment. So AI is more mass scale. So that's where this methodologies come in. So importance of AI in ophthalmology is that it enhances the diagnostic accuracy. It's much more scalable. It helps monitoring disease progression. Like it's very good at time series data, like progression, prediction of onset, etc. And it's cost effective because for triaging, you don't need a doctor there, right? You just can take a patient's image and then we can find out referable versus non-referable people. So now, what is the need for federated learning in ophthalmic diagnostics? A major limitation for actually the clinical deployment of these AI algorithms is the need for large amount of well-curated data sets. And well-curated and labeled data sets. And there are numerous barriers to building and hosting these large central repositories and multi-institutional data sets because there's concerns about data sharing, compliance, regulatory issues, and hospitals are generally very strict about sharing their data. So there's a clear clinical need for a robust AI model training framework that can leverage this multi-institutional data without compromising these data sharing concerns. And that's where our lab thought about using federated learning or distributed approaches to see if we can really use federated learning for ophthalmic diagnostics. It can provide data privacy and security, access to diverse data sets from subpopulation spectrums. It can allow collaboration without really sharing the data, optimize some of the resources, real-world application scalability, because now you have a robust model that can be tested in different settings. So that brings into the first project that I'm going to talk about is the real goal was basically to see if federated learning models how they compare against local and central models. So objective was basically identifying AMD versus non-AMD patients using a bunch of public and private data sets. Fortunately, there are a couple of open source data sets in OCT shared by researchers. And then we have collaboration at North Carolina with Wake Forest, and then Illinois and Stanford, where we got a bunch of OCT images with a wide spectrum of AMD labels. So some example of AMD patients we can see here, pathologies like this is advanced dry AMD, which is GA. You can see a tumor-like thing here. And there's also wet AMD where there's like a fluid accumulation in the patient's eye. So so the general framework, so we did use Flower as our framework, and then the general framework is probably known to most of you. Is basically we treated each of the data sets as a separate node, and then there was local model that was trained on the local data set, and then the parameters were updated and aggregated globally, and that parameters were shared to local data sets. And we found out that, and we also tried different aggregating methods, like not only just averaging, tried FedProx, SR, MRI, APFL, etc. And we tried different models to compare the likes of like ResNet, GoogleNet, and more larger network like Vision Transformers. This is published in this paper, so if you're interested in reading more, feel free to take a look. The summary is basically we saw that the federated learning models outperformed each local model, and even were comparable to a central model, where a central model had access to all the data sets. A federated learning model did not have access to all the data sets, but it has access to the parameters. And aggregating methods do affect the performance, because we found out that some methods worked better than the others. And we also found out there's a need for domain adaptation, which is a really important factor in using federated learning for medical applications. We saw that because each institutions, for example, Chicago has more African American population, Wake Forest has more white population, Stanford has more Hispanic population. So we saw that because the data set is coming from different subpopulation spectrum, there are some issues with the federated model converging. So I think in our future work, we're planning to work on some domain adaptation methods where all the domain can be converged into a singular domain. The next project was basically using the same methodology for multi-class. Here, the challenge was because we didn't have overlapping labels in each institutions. For example, I am doing a 5-class classification for 5 diseases or 5 stages of AMD. Not necessarily all the institutions have the same labels, and we didn't want to have that because that's the real-life clinical scenario. So what we did is we used a self-supervised method called mask image modeling, where we pre-trained all of our data sets in a federated learning manner. And we pre-trained to mask part of the images and then train a model to reconstruct that. Our hope was that would give us a nuance learning of the model of those images coming from different labels. And then we use that final, the weights and fine-tune that on for different particular tasks. And this was the framework. Basically, all the institutions contributed to MIM training. And then final FL aggregated model was used for fine-tuning. And the result summary was, we're still kind of this ongoing work, is that we also saw that the federated learning models outperformed each local model for multi-class classification, even if when each local institutions don't have all of the labels. And the MIM weights really improve the performance compared to generic weights. There's also need for domain adaptation there. And in our future work, our question was, can we replace this kind of self-supervised methods and use just federated learning for multitask learning? I think Virginia was talking about multitask learning. Some of her work has explored this. And this is something we're planning to do, for example, using data maps or task tagging to see if we can just use federated learning domain for multitask learning. Some of the challenges that we have faced in applying federated learning, especially in retinal images, is that the device oftentimes is not device agnostic. Like device and acquisition protocols in retinal images actually affect the performance, patient demographics, and sometimes there's an issue with privacy versus accuracy, and all those. So these are probably the research directions that we're gonna follow in the future. And that's all I had. Thanks so much for having me here, and I'll answer any questions. And thanks to our collaborators, and we have been recently funded by the NIH, so I'm really grateful for that support. Thank you.
Thank you so much. So we have time for a couple of questions, if they're in the room or online. We've got one question here immediately.
Hi, thank you very much for your presentation. From the patient's perspective, what's the benefit of using these kinds of AI detection for AMD? Once, as far as I know, it's not really curable. And would it be interesting to explore in the future how well AI federated learning can predict the evolution of these patients? Thank you.
Great question. So AMD is technically, there is some interventions there. For example, you can provide anti-VEGF injections, which is basically actually a huge area of research to predict how many anti-VEGF injections you need to provide for a patient to get better. For example, if you can see some of the images of AMD, like this one, there's fluid accumulation there. So if you provide this injection, this goes down, becomes like normal. So AI can predict, for example, from baseline, how many, and it's almost like chemotherapy. Like some patient really responds really well and they get better, and some patients don't. So it's very important to have diagnosis, early onset predictions, and also prediction on like how many anti-VEGF treatment a patient might get. I would say, so AI modeling is important. And for federated learning, I feel like it's very important because federated learning is democratizing these models. For example, if you're at Stanford, then you have millions of images anyway, so you don't really don't need federated learning. But say if you are in a smaller institute which doesn't have enough data by itself for training a model, then if you are part of that consortium, right, federated consortium, then by just being part of that, you have access to a more robust generalizable model. So that's how these institutions and then the patients are being helped using these models. And then, so the second question, you mean evolution is basically, I think you're in the realm of personalized medicine where you're tracking a person by themselves. So basically the first step would be to triage and identifying the person's stage. And then you go from, for example, you would see all of their prior visits and try to predict different things. For example, for this patient, you might be able to use AI model or federated AI model to predict the response of that person to this kind of intervention. So then you are in the realm of treatment management and personalized or precision medicine, basically, which are all very interesting fields of work, and people are pursuing them as well.
Great. Thanks so much. I think we might have run out a little bit of time to carry on for the next question. But thank you so much for the talk. It's a wonderful talk, wonderful bit of Q&A just in too. So thank you very much.
Thanks, everyone.
So our next talk is about a critical issue in the world of federated learning, and that is about data sets. I can think of no better person to talk about what we can do in terms of advancing federated data sets than my colleague Adam. So over to Adam.
Hello, everyone. Let's talk about the data in federated learning. It's an essential part, and typically we see it naturally distributed. but we are talking about the research. Therefore, we need to partition data set. We might encounter two different types of data set, either with naturally existing ID, identifying, for example, a speaker or a machine, or we'll need to completely partition the data set that does not have a notion of an object. That process is typically time-consuming. We do not have libraries, didn't have, that would allow to do that in a seamless way or without copying the code. And we heard many people struggling with that process, especially beginners. But yes, to better understand it, we might have a look at the data preparation workflow. So you would find a library that has the data set in a centralized way. You'll download it via the library, or if you didn't find the library, maybe you need to have a manual download, figure out the partitioning scheme by going through the papers and trying to figure out the details yourself, implement it, partition the data set, and then if you're lucky, you'll also have some time for testing. Oh, I see, it was a joke. Problems with custom code. Well, we have actually some problems. It's time-consuming. It might lead to limited adoption of your work, and it's error-prone. That's for the creator. Then we have the reader. For the reader, it might be hard to understand, hard to extend, hard to reproduce. It's framework specific and it has limited documentation. That all makes that process for both creator and reader quite a challenge. The solution, I'm happy to announce Flower datasets. That's the library that allows you to seamlessly download, partition, and do any kind of pre-processing for federated learning that you'll need. It solves the problems that I mentioned, and I want to go one by one and tell you how. Firstly, that's the whole code you need to partition the dataset, and in that example, I'm using Dirichlet partitioner. We have two abstractions, and I'll talk in more details about them. It won't be time-consuming when using Flower datasets. It's hard to understand, and the custom code. Let's understand how Flower datasets works. We have two abstractions, federated dataset and partitioner. Here's how you create federated dataset. You have the dataset, give the dataset name, and you specify partitioners. Then you're ready to go by doing just load partition and giving the partition an ID or loading the full split. Some of the things I'll clarify in more details later, so no, don't worry. And we have partitioner. Partitioner is an abstraction that, as the name suggests, does exactly the partitioning, and it's customizable, and we provide many of that abstraction. So federated dataset will take partitioners in a specific format and download the dataset and do all the steps that you will need for your experiments. And I'll talk in more details about it. Hard to extend, yeah, so let's do some basic math. In order to determine how many datasets, how many federated datasets we can create, let's just loop over all the partitioners that we provide. Each partitioner might come with suitable, accessible dataset. So suitable if you want to use natural ID partitioner, but you use dataset without the ID, of course we cannot count it. And so that's the suitable. And accessible is the part, well, the library allows you for limited number, typically, of datasets. And we have configurations. So each of such partitioner can be configured in a specific manner. You can have the alpha parameters, number of partitions, partition sizes, and things like that. So if we have same API for dataset to make it, for the library to make it understandable, we can have all the datasets downloaded easily. So let's see how we can how we go for that number, how we derive it. Here is just the name that you pass. And if you're going from, for example, NIST to Cipher 10 or whatever, that's the whole difference when it comes to the data set. And Flower Labs uses Hugging Face under the hood. So you go to Hugging Face, go to the data sets, you type in the name of the data set, and you might find that there are over 100,000 data sets available there. You pass that name there, and you're ready to go. So here is an example of NIST. You copy that little thing, the name that you find in the orange box, and you also have the preview of the data set on their website if you want to check it out prior to doing your experiments. Partitioners part, right? How do we go with that number high? We allow each partitioner, each federated data set to have multiple partitioners, and we pass it as split to partitioner. Let me explain in more details. Partitioner, you'll create it, instantiate it out of many out-of-the-box partitioners that we have, or create your custom one. And you'll give a configuration, just like, for example, train split will be partitioned according to the partitioner that you just instantiated. Then you just go load partition, give partition ID, you're ready to go. That's the part that will change. IID, shard, Dirichlet, and many others. Oh, natural ID, yeah, if a data set allows you. Well, flexibility. Let's talk about more the configuration of the data set. Data set comes often with some predefined splits. That's how they are also represented in Hugging Face. You might typically find data set with train and test split. That's the division that was created typically for centralized machine learning. What we allow you to do is, if you want, you can just go and you can also grab one of that splits for example, centralized evaluation. What you can do is you can also resplit the data set. So train test to your new train test that, for example, contains 60-40 instead of 80-20% of the data. It's up to you. Well, let's say you want to partition the train part of the data set. What do? Yeah, you pick it and you assign the partitioner. A little bit of notation that will be useful later. Each partition can be further divided. For example, if you have on-edge train and on-edge test, for example, we will call that thing divisions. And we also provide functionality, coming back to the centralized thing. For example, if you want to create a centralized data set out of the test, let's call them, or evaluation parts of the data set of each of the partition that you create. You can also do that thing quite easily, just one line of code. So you choose, for example, in that case, if I specify the list 80-20, then if I pick the division ID 1, it will correspond to that little thing that is that has orange box around it. So we have the centralized dataset creation also enabled. Just coming back maybe, partitioner, you'll create, for example, train, and you create a Dirichlet partitioner to partition the train split of the dataset. What you can then do, you're not limited to using a single one. For example, if you plan to use only certain devices for training and other for evaluation, not splitting the dataset on each partition, but making, for example, sure that only certain clients are used only for test and other for training, you can do it too by creating a dictionary that maps many of the splits that you create or resplit and create and allows you to partition it also according to, you might choose different partitioning schemes. Here we go, framework specific, and that also goes with limited adoption. And it's definitely not the case because you might create your new partitioner by simply subclassing the partitioner abstraction unit, load partition basically method, and you create the indices or whatever you need in your custom way. It seamlessly integrates with the whole federated data set, and regardless of the type, modularity of the data that you'll choose. And it's open source, so whenever you create your work, you can also create a pull request and have that in our library and let other people enjoy it too. Well, we go framework specific. So typically what you'll find is once you download it and partition, it's, for example, if you're a PyTorch fan, you'll do it in PyTorch, NumPy. Here we allow you to use any of the following. So TensorFlow, PyTorch, JAX, Hugging Face, NumPy, Pandas. It comes by default with Hugging Face dataset, and yeah, that's the abstraction on which the partitioning happens. But it allows you to use your work across different frameworks. And it's important because we have the same data source regardless of the ML framework of your choice. Therefore, it makes your work also easier. No need to create the same thing, but to just use different framework. Yeah, so let me back it up. Here is how you do it to transform to TensorFlow dataset, one-liner. It integrates with TensorFlow transforms. Here is how you can do it. NumPy, one line. Pandas, one line. Well, that was framework specific. Hard to reproduce. We have the seed mechanism that makes sure that order or any kind of operation that is random, you have full control over. Well, limited documentation. You're welcome to check the documentation on flower.ai, Flower datasets. Error prone, it's throughoutly tested, so you have unit integration test and constant GitHub CI. So you might be sure that you can be sure that the data set that it works what it does. Well, yeah, the time ends up. I'm Adam Narożniak. I'm a data scientist at Flower Labs, and here is how you can download the library, pip install Flower datasets, vision, audio, or without the thing for any CSV or any other thing that you need. Thank you, and yeah, questions?
Thank you for the talk. We'll take one quick question from the audience, because that was pretty important material. Yeah, from this guy down here. Thank you. What's your name? Daniel. Yeah. All right. Okay, Daniel.
Thank you.
What's your question?
Okay, thank you very much. Hello, Adam. Pretty nice job indeed. My question is, in the future pipeline, do you consider to include also feature skew and quantity skew? I mean, you are already working on label skew properly?
Yeah, definitely, and everyone is also welcome to contribute, and we'll try to follow up also as the research follows. We'll be happy to simulate any kind of heterogeneity that someone comes up with.
Perfect. Thank you, Adam.
Thank you.
So our next two speakers flew in from China to give us a really interesting talk. Bing Liu is the assistant professor of data and computation at Duke Kushan University. And what I really like about his lab is I think he's one of the leading labs in China in the domain of federated learning, and he likes to use Flower. He's going to be telling us how he and his student Stephen are going to tell us how they're going to build out this vision of a Fed campus. So there's going to be a smart campus. There's a smart campus that is built on privacy-preserving infrastructure using federated learning techniques. So thank you for coming so far to give us this talk, and over to you.
Thank you, Nick. Hello, everyone. Really happy to be here and present our project, Fed Campus, at Flower.ai Summit. So join me here today is my student, Steven. So, and I don't know whether he's the only undergraduate student here in this room. So he's a senior student. Probably he will join a PhD program this fall. But he haven't decided the which PhD program yet. So, okay. So for today's agenda, so in the first half, I will briefly introduce some of the Federated Learning research work I have been doing, and also my group has been working on. And then I will talk about, briefly talk about the Fed Campus project overview. And in the second half, Steven will take over to talk about the system development part in Fed Campus. Basically, he will introduce 3 key challenges in terms of the system design. Okay, so Duke Kunshan University. So here, probably you may not heard about this university. So it's quite young. So it's been established in the year 2013 in Kunshan. So it's as a U.S. and China partnership between Duke University and Wuhan University. So one of the key features of our university is that we will offer Duke degrees, both graduate and undergraduate and graduate degrees. So, a couple of words about my lab. So I lead the Duke, DKU Edge Intelligence Lab. So my research interest mainly about Federated Learning and analytics, and also AI-powered mobile and IoT systems, as well as game theoretical, like computational game theory and incentive mechanism design, especially in Federated Learning. So those clients, they are not belongs to the company or the system. So you may need to design the incentive mechanism to attract the clients to join your federation. And so the research in Federated Learning in my group is mainly focused on how to address the challenging statistical and also system heterogeneity, because those two heterogeneity are coupled in terms of the different clients. So when you design your algorithm, you should consider both the data heterogeneity and also the system heterogeneity. System, I mean, like different clients, they may have different computational power and communication power, and also the unstable issues. So, so here, this slide summarizes some of my research overview in Federated Learning. So our goal is to enable effective and efficient Federated Learning at future network edge. So when you deploy Federated Learning at future network edge, so how to make sure the model works, which means effectiveness, and also if it works, can we do it more efficient way? So here, efficient, we mean both time efficient and also energy efficient. Some of the works like using the methodology like optimization from system parameter control to make sure when you deploy Federated Learning algorithm, you can achieve both time efficient and energy efficient design. And also adaptive client sampling, focusing on different clients, they may have different priority or importance. And third work is about incentive mechanism, right? So how to attract, how to incentive those clients to join Federated Learning. So you need to consider, if you want to design a mechanism, you really need to consider different clients, what is their contribution level to your Federated Learning model. So you may design different price, different payment strategy for different clients. And also different clients, they may have different interests about joining Federated Learning. If I really care about this model, I may join without even you pay me, right? But if I'm not really care about this model, but if you want to use my data, you want to use my training resources, so you need to pay me. So this is about incentive mechanism. And last work, this is really about today's presentation about Fed Campus. So instead of theory and game theory works, we also we have also done some system development in terms of application app. So Fed Campus. So the overview for Fed Campus is what we really want to achieve is we want to analyze our university's health data in terms of both students and faculties. for example, we want to analyze what is their sleeping patterns, their exercising time, what is their pressure in terms of heartbeat and you know, the heart rate, so related to the anxiety and pressure. So this is related to the health data. Other applications we have been doing is try to analyze in the campus level what is the heavy hitters like the popular words, popular song, and also some GPS-based heat map like the different populations trend. So that's the basic overview of FedCampus. So our project wants to target two kind of audience. So first, the users, like the students' point of view. From the students' point of view, students may interest about others, like peers' behavior, without revealing its own private data. And also, another perspective point of view is from the administration of university level. So the university may want to know students' health and well-being conditions, like the anxiety and pressure variation during exam period or before the exam period. So that they can adjust like the teaching load and make some suggestions for faculties. So that's the two target audience. So here's the short video which really captures the FedCampus.
As a student, it's intriguing to see how my fitness data compares with my peers. When do they sleep? How long do they usually spend in exercising? For university administrators, tracking health trends and ensuring students' well-being is crucial. How are students' pressure level and sleeping pattern vary, especially during the exam period? How can we analyze and learn population's health data while protecting individual sensitive and private data? The challenge is to comply data privacy regulations. To address data privacy challenges, here comes in our FedCampus a privacy-preserving data platform, a smart DKU. With privacy-preserving technologies, differential privacy in federated learning. Differential privacy carefully perturbs sensitive information while providing valuable statistics trends. For example, when comparing your sleep quality with others, differential privacy ensures that individual sleep patterns cannot be traced back to a specific user, unlike traditional methods where user data is centrally analyzed. Federated Learning enables FedCampus to leverage multiple devices like smartphones and smartwatches for decentralized data processing. By analyzing data from various sources, FedCampus can tailor fitness recommendations aligned with your health goals. You get the benefits of customized fitness device without exposing your sensitive information. Supported privacy-preserving techniques. FedCampus is your personal health assistant. It prioritizes and respects your privacy, empowers you to make smarter health decisions. With FedCampus, you can monitor your daily health metrics to know your ranking in the population statistics without privacy leakage. FedCampus also provides a feature to view your percentile rankings with privacy safeguard in areas like daily steps and carbon emission reduction, supporting sustainable campus lifestyle. FedCampus also features comprehensive overview of the campus health statistics. After our several rounds of lab internal tests, we successfully launched our FedCampus project at DKU and distributed 100 smartwatches to volunteer students and faculty, empowering us to build a privacy-preserving health data ecosystem at DKU. As FedCampus evolves, we aim to build a privacy-preserving data ecosystem.
Okay, so that's the video, and so before I introduce my students, so here, so I want to share that this is the reason why normally I will wear two watches. So that when people ask me, okay, why do you wear two watches? So I can introduce our project. Okay, so now, Steven.
Thank you. So I think I have 4 minutes. Let's go look at how the implementation of federated learning in FedCampus works. by boiling it down to 3 challenges, really. The first challenge is how we can locally access the training data. Maybe we can just use Flower dataset, and there will be one-liner. Except no, the data is generated on the smartwatches and synchronized to Huawei Health, from which we will need to access the data using Huawei Health Kit API or Apple Health Kit API. And this is one of the challenges. Their APIs are not really good to use. Then we have the data on the app. We pipe them into our Federated Learning SDK, and the derived data, such as parameters, are sent to our backend. This means that we need to make an app, and mobile development is also a huge burden. In this app, we need to do several things. This app is the way we access local training data on the smartphone. It needs to be cross-platform. That is, we support both Android and iOS. To do this, we chose Flutter. And so far, it has been a good choice, plus the nice UI library they provide. The second question is, how do we train the models on the cell phones? Initially, we thought it would be easier if we use a Federated Learning service. So we found a company and tried to integrate their SDK into our app. But it turns out the way Federated Learning services work is they send the data to their servers, which is a deal breaker because it doesn't pass the IRB among other reasons. So we turned around and looked at open source solutions, and obviously we found Flower. On top of Flower, we built FatKit, not to be confused with FatKit. In short, what it does is it trains the model across Android and iOS through this pipeline, and it does machine learning operation in this case, which it basically means it trains the model, it trains the latest model, deploys them without needing to update the app. This is done with Django and Flower. Check out our poster downstairs, by the way. And in this process, I was fortunate to contribute the new Android example and iOS bug report upstream. This one is merged, and this one is solved like 2 days later. Props to the Flower team. The third challenge is when to train the models. This question might be a bit more surprising, but it comes from the reality that the users control their smartphones, not us. What Gboard did and everyone was looking at was they trained the model when the user's phones are idle, but it didn't work for us because the background jobs we implemented did not run. After asking some people from the industry, we got to know that many versions of Android don't comply with the spec, and they just don't run the background job. So instead, we have to do some workaround, which is tell the users to leave the app open for 5 minutes a day. This also brings us to an important takeaway. That is, if you are not Apple or Google, you probably need to do this. So that pretty much sums up all the challenges we have in implementing Federated Learning in Fat Campus. I hope this has been helpful. Thanks.
Thank you both for the great talk. We can take one very quick question. Does someone have a quick question? Yeah, at the front.
Thank you for your presentation. So my question is, which kind of model you implemented on the smartphone, and yes, which kind of model? Which is the complexity of the model? Thank you.
So, thank you. Thanks for your question. For the facial learning on smartphones, so we deployed a very simple, like sleep efficiency model. So with the training data set from our users' sleeping data, and also because if you want to give a sleeping efficiency score, so not only the sleeping hours, but also some other kind of data, so you can initiate like a simple linear model, so based on some of the data. For our facial learning model, so we just deployed a very sort of a simple linear model. Yeah.
Thank you. Thank you.
Yeah.
Great. That's all the time we have. Thank you so much for telling us about FedCampus.
Thank you.
So our next talk is by Judith Sanchez Pardo Diaz. She is a data scientist at the Spanish National Research Council, and she'll be telling us about a pretty interesting platform that they have built on top of Flower that enables around 50 scientists, so 50 scientists do basic research, non-computer science, but in the kind of like different fields like chemistry and so on. It's a platform that allows these 50 scientists to use distributed data for doing their types of research built on Flower. So thank you so much for joining us today, and we're really interested to hear what you have to say.
Yeah, okay. So thank you very much, Nick, for the presentation, and thank you very much to all the Flower team for the invitation to talk about the implementation of federated learning within the European Open Science Cloud. Sorry for the slides. And I would like to start by explaining what is the European Open Science Cloud, because probably most of you didn't know this ecosystem. And let's start by the objectives and the roadmap of the European Open Science Cloud, the EOSC, which aims to develop the web of fair service and data services in order to enhance the science, the reproducibility, and the digital transformation we want to perform in Europe. So the implementation is a long-term process which is aligned and coordinated by the European Commission since 2015, and currently, in the current phase, which is between 2021 and 2030, we are moving to a more, let's say, a stakeholder approach in which we want to share a common vision, common objectives, and all in all, perform complementary contributions at both the European, the national, and the institutional level. Also, I would like to note that although we say the European Open Science Cloud is not a cloud, and the EOS is not a cloud provider, and it also doesn't own the data or the services that are involved in the products, but is an enabler of that science that we are doing. And why are we interested in the EOS? What we want to achieve with this ecosystem? First, we want to improve the scientific research that we are doing, and in order to do so, we want to facilitate it by accessing to to a greater amount of data sets, to a great amount of research results, which are quite important to improve the scientific research that we are doing in different fields. So we can be talking about chemical, about medical imaging, about a quite different diversity of data. Also, we want to foster the innovation that we are doing, and in order to do so, we want to enhance the collaboration between researchers, to publish in open access, to share, to build into others' work, and also in the same line to improve transparency and improve the reproducibility of the research that we are carrying. So also, another of the objectives is to reduce the duplication of the efforts, and in order to do so, we need to encourage data sharing and data reuse. And all in all, this will facilitate the interdisciplinary research and also the cross-sector collaboration. And now I will talk about the artificial intelligence for the European Open Science Cloud project That is the main objective of the talk. And this is a project which is funded by the European Commission, by the European Union, which runs from September 2022 to August 2025 during 3 years. And within this, during this project, we want to provide scientists, we want to provide the users of the AI4Us platform, which I'm going to show later, with advanced features to perform distributed federated learning. Of course, we are talking about federated learning, so of course distributed and federated learning, but also other tools such as machine learning operations, such as metadata provenance, and so on. So in this slide here, you can see the 5 main objectives of the project, and I'm only going to focus on the second one, with which we want to support scientists to build AI systems, to build AI models, of course, machine learning, deep learning models, which can be trained on distributed datasets. So we have a particular focus on federated learning for this task. And in order to do so, we are using Flower for implementing the support for the federated learning part. Here you have the high-level architecture of the platform that we are implementing. And here I just want to focus on the part of the federated learning. Here we have Flower as the framework that we are mainly using. But you can also know the different development environments that we are providing to the users. The users can develop their models both using, for example, Jupyter Lab, that is quite common, but also Visual Studio Code, and we are working on these development environments. Here you have the diagrams of the architecture, if you are interested, in the C4 model, which is quite, let's say, intuitive and accessible and interactive, of course. I have included this slide just 5 minutes ago in order to show you what is the AI4Us dashboard, because I have noted that I'm explaining the AI4Us project, but if you are scientists and want to use the platform, what are you going to find? So when you log into the platform, you have the different modules that are pre-trained modules with different AI, with different machine learning, deep learning models. For example, one image classifier, one audio classifier, and other modules applied to specific fields. For example, here, to classify conus species, to classify plants, etc. So this is what you can see when you enter the marketplace. But I want to focus on federated learning, and let's move then to how are we implementing federated learning in the platform. So first, when we start implementing federated learning in our platform, we encountered one problem, which was related to the server and the proxy that we were using. So I'm going to be quickly into this, but as you know, with Flower, we are using gRPC, and in our case, the gRPC server was running behind a proxy, in our case, Traffic, which acts as reverse proxy. In this line, the clients may not be able to connect with the server, so we perform some modifications to the Flower library that the solution that we propose is already included in the current version of Flower, so first problem solved. Then on the other hand, we find other problems when talking with our use cases, with the use cases that are on board in the project, and we thought about problems that can arise when different attackers act as clients. I mean, for example, let's imagine that we are working on creating a server and different clients, which are, for example, hospitals, want to create a machine or deep learning model and train it, a global model, using this federated learning server. How can we know if a different client which is connected is or not an attacker? So we decide to implement the authentication. So if we are acting as the server, we will need to give the different clients a password, let's say, a kind of token or secret that they will need to enter in order to be able to connect with the server. So only authenticated clients can connect with the server. In other case, all the clients that have the IP in which the server is deployed will be able to connect to the server, and they can even perform a poisoning attack. So in order to implement this part, we first implement what we call AI for Flower, which are some Flower extensions in which we include bearer tokens for allowing the authentication. We also perform a modification in our own AI for EOS Flower repo, in which we aim to manage the credentials that are needed in order to perform the authentication. And we also created a system for storage management. We use it Vault, which is from HashiCorp. I don't know if any of you know it, but we implemented it, and we integrate that system in our, of course, Vault is already created, and we just introduce it in our deployments. So let's take a look on how can we perform a federated learning training within our platform. First, our main objective is to make federated learning easier to scientists, make it accessible to scientists, and make it more easy to use. So when you join the platform and want to perform a federated learning server, this is what you can see, federated learning server that will be deployed with Flower, and you just need to launch this tool. And you will see that there are some general steps, some general configuration that is quite intuitive, is quite user-friendly for the users, because first we have the general configuration in which we just need to introduce the title of the deployment, which will be the title that we have to identify our server, the description, and the service to run. Here we can select between Jupyter Lab, as I have already explained it, or between Visual Studio Code, or just federated server will be a terminal for monitoring the process. Then we have the hardware configuration. In this case, as we are just starting the server, we don't need, in most cases, specific hardware requirements. So just here we have the CPUs, RAM memory, and disk memory. But in other cases, for example, when we are starting the clients, we may need to have some GPUs and so on for training the models. And the last step is the most important one, because here we can see that the users do not need to interact directly with the code, with Flower and with any code, because here the user just needs to introduce the number of rounds of the federated learning training, the minimal number of clients, the evaluation metric that he or she wants to use, more than one if needed, and the federated aggregation strategy. He or she can select between different aggregation strategies in order to run the federated learning server. And then we get our deployment, which is here, which is running, and we can see how can we start the server. Quite simple, just by running Python 3 fed server server.py. Then we have our federated learning server running, and we don't need to change anything in the code. It's already configured with these parameters. So I have already talked about the secret management. So in order to perform the secrets management system, we have here how can we manage the secrets that we have created for this server. And we can add new secrets. For example, let's imagine again the case in which several hospitals are collaborating. Then if I'm the server, I will send to the first hospital one token, one kind of password, let's say, for he or she to connect, and the same for the other clients that are authenticated, that are involved. But in case that I have an untrusted client, then I can revoke the secret, and that client will never be able to connect again until I send them another secret. So this is our secrets management, and we can create more, revoke secret, and so on. Again, here, this is quite intuitive because we all have been working with Flower, so we can create in a virtual machine. In this case, for this example, this is not in the A4US platform, although we can do it in the platform, but here I have created a client in a virtual machine in our own cloud, in our own data center. And in order to connect, when we want to have the server deployed in the platform, we just need to introduce the endpoint of the server, which is here, and the token that we have implemented here with AI for Flower, bearer token. So we just enter here the token, and we are able to connect. We can see here in this function from Flower, from start client, you can see that we have entered a new parameter, which is called credentials, and is the parameter that we use to authenticate the connection of the clients with the server. And this is the classic approach that we get when we are training a federated learning model with Flower, but you can see some things that are new. For example, here, all this part is regarding the service of authenticating the clients, and then we have just, as usual, the federated learning started with Flower, and we are requesting initial parameters, and so on. And from the client side, the same, we have the same configuration, but first we have here information regarding that, the token that we are using to connect with the server. So in order to conclude with the A4US platform, just as conclusion, we can show how we can train a federated learning model and perform it with the server deployed in the platform. The clients can be allocated, for example, in other cloud machines, can be allocated locally or even in other deployments, also in the platform. We can use Visual Studio Code or Jupyter Lab as we wish in order to modify the code if needed. And we have implemented different extensions to the Flower library. The most important one that I have already shown is the one concerning client authentications, because we have implemented this secrets management system in order to allow only authenticated clients to connect with the server. So here you have the code for accessing the platform if you want to check information about it. You have here the web page, and we are going to launch soon a call for external users, for any other scientists who want to collaborate. And with this, I want to finish by just mentioning that the wide variety of use cases that we have, for example, agrometeorology, for example, automated thermography, integrated plant protection, medical imaging, and so on. So I expect that this is interesting for you, and thank you very much.
Thanks so much. I really love the fact that this is going to be enabling for scientific breakthroughs by allowing people to use distributed data so much more easily. We have time for one quick question. Sure. 1 second.
Yeah, so my question is that, so I think to ensure that only honest participants are there in the system, so you have done something like a key, you have used some maybe big key, but the key is normally can be leaked even by the honest participants. So in the future, are you planning to do something like a public key encryption, or maybe using something like a blockchain to make sure that it is more foolproof and maybe better than maybe using a single key only?
Yeah, it's a good point. But here, for example, I was talking about the case in which we may lead with clients that are not authenticating and want to poison the model, which is more common as we can expect because we have seen some examples. And it could be the case, for example, as I have mentioned, let's imagine that we are working on training a model for medical imaging, and one attacker joins a client and train a model with images from cats and dogs, for example. That will be damaging the global performance of the model, and that's what we want to avoid in some case, but just allowing authenticated clients to join the training. But that's also a good point that we will take into account. Yeah.
Great, great. Well, thank you again. Thank you so much for being here and your talk. So we're going to conclude our proceedings for today with a special announcement. It's really my honor to give a tiny talk about a really big technical milestone. And that milestone is called Flower LLM. So what is Flower LLM? Well, it can be summarized very briefly. It is both a model and a methodology that's enabled us to do this. We have produced the world's first 1.3 billion parameter LLM. This is a pre-trained model. It's not fine-tuning. It's not an adapter. It's a raw LLM trained in a federated manner at a size that's never been seen before. And Flower LLM brings together two really critical pieces of technology that is shifting the landscape of machine learning. The first of these, of course, is federated learning. By the fact that we've been able to prove that you can pre-train an LLM using federated learning methods, it enables anyone to combine a mixture of GPUs together to produce arbitrarily large compute to train increasingly big models. Furthermore, it allows you to access data that has never been able to be trained on LLMs before. And so by bringing the worlds of LLMs and federated learning at a fundamental level, that of pre-training, we are doing two things at once. We are democratizing LLMs in a true sense. It's not a question of open sourcing weights or allowing a series of open source training recipes. It enables organizations, individuals, companies of all sizes to combine GPUs together to train the very largest models on the planet and to leverage the type of data that doesn't only exist in the web but exists in the real world. And for that reason, it also enables us to push LLMs fundamentally even further. Because once you can start to combine GPUs together in this manner, you can increase the parameter size. Once you can start to access larger and larger amounts of data, this will result in stronger LLMs fundamentally. If I start to think about the nearest result that is currently available, it's a slightly unfair comparison to that of Flower LLM. That's because it's not a pure federated solution, but the nearest one is a result from Google DeepMind. They managed to train a model that was around 400 million parameters, but this result here is more than 3 times larger than that under a tougher training recipe. If we break down this very briefly into seeing different varieties of Flower LLM, because this is not just a model but a methodology. If you can compare the DeepMind model to that of our largest model, you can see that we're able to train a model at 1.3 billion parameters, but maintaining the same demand of GPUs. We've got the same amount of clients per round and the same tokens trained, but the model parameter size is, again, 3x larger. If you compare the nearest varieties of these models, which would be the DeepMind model against Flower LLM Medium, you can see that we're training able to train twice as many clients and twice as many tokens trained. This is a product of an enormous amount of engineering and research work. So it's a collaboration between Flower and academics at the University of Cambridge that have been able to pull off this mammoth milestone in the world of federated learning. After this announcement, there will be a blog post that summarizes this slightly in more detail, and then following archive paper that fully encodes and describes how we've been able to do this. But a natural question is, where to next? Well, I think that this result aligns strongly with a series of open source models that have been produced in the last 12 months, especially those that exist between the 1 billion to 10 billion range. But what is fascinating about Flower LLM is that it's creating a brand new category within this space. It's not correct to compare these directly with the models from Mistral, from Microsoft, Mosaic, and the like, because these are federated LLMs. These are trained, every other model I just described is centrally trained. This model is a product of a combination of various types of GPUs woven together, and with the ability in its training approach to use data at those different isolated locations. So the next steps are that we believe that this method will scale to 30 billion parameters, and this is a conjecture that we'll be demonstrating and proving over the next 12 months. But most importantly, as soon as humanly possible, we will be releasing the source code available to everyone. It's built on Flower, but contains many technical tricks to enable it to be possible. But the key idea here is to let anyone do this. And so we'll be endeavoring to do this as fast as we can. That's the announcement. Thanks very much. That concludes day 1 of Flower Summit 2024. For those of you physically here, we are going to have our after-hours event across the street that starts basically from now. For those of you who have joined us online, thank you so much. We'll be starting the same time, 1 p.m. UK, tomorrow for AI Industry Day. Thank you, everyone. Thanks very much.